Hello and welcome to Sleepy Science. Tonight, we are going to explore one of the quietest and most powerful mysteries in the universe, black holes. They are often described as monsters, cosmic drains, or holes in space. But the truth is stranger, calmer, and much deeper than that. A black hole is not simply a place where things disappear. It is a region where gravity changes the meaning of distance, time, light, and information. Near a black hole, the fastest thing in the universe can lose every path outward. A clock can slow compared with clocks far away. Matter can glow brighter than galaxies before crossing into darkness. And the surface of a black hole may carry clues about information, entropy, and the hidden structure of reality itself. In this journey, we will move slowly from the simplest question, what a black hole really is, into the deeper edges of modern physics, where stars collapse, light bends, space-time vibrates, galaxies evolve, and science begins to ask whether the universe ever truly forgets. The strange part is not only that black holes exist. The strange part is that they force us to rethink almost everything we thought was stable. Before we go deeper, let me know in the comments where you are watching from and what time it is there right now. It is always fascinating to imagine people around the world listening to the same dark cosmic question from different corners of the night. And if you enjoy calm, mind-opening science like this, please take a moment to like the video. It helps the channel grow, and it tells me that you want more long, quiet journeys into the deepest mysteries of the universe. What a black hole really is. A black hole begins with a quiet misunderstanding. It is called a hole, but it is not an empty opening cut into space. It is a region where space-time itself has been bent so deeply that every path inward becomes easier than every path out. Think of the universe not as a flat stage, but as something flexible enough to curve around mass. A planet curves it gently, a star curves it strongly. But when a huge amount of mass is compressed into an extremely small region, the curve becomes so severe that beyond a certain boundary, escape is no longer possible. This does not mean the black hole is a magical drain, or a doorway to nothingness, or a monster with hunger. It means gravity has become geometry. The black hole is not mainly a thing with a surface you could touch. It is a place where the rules of motion have changed because space-time has changed. Far away from it, gravity behaves normally, like the gravity of any massive object. But close to it, all possible routes begin to tilt inward, as if the landscape of reality has become a valley so steep that even light cannot climb back out. That is what makes a black hole so strange. It is not dark because it is painted black, or because it absorbs light like ordinary material. It is dark because light that crosses too far in cannot return to your eyes. And this teaches something deeper than a definition. It shows that space is not just emptiness. Time is not just a clock ticking in the background, and gravity is not simply a pull you feel beneath your feet. In Einstein's view, gravity is the shape of space-time, and a black hole is one of the most extreme shapes nature can make. It is a place where the universe folds its own pathways inward, hiding whatever lies beyond from the outside world. So when you imagine a black hole, do not picture a simple pit in the cosmos. Picture a silent region where mass has changed the architecture of reality itself. Picture darkness not as absence, but as a sign that space-time has reached a limit your ordinary senses were never built to understand. And perhaps that is why black holes remain so powerful to think about. They do not only challenge what we know about stars and gravity, they remind you that reality can be much stranger than the names we give it. Why black holes are not cosmic vacuum cleaners. The fear begins with a simple mistake. People picture a black hole as if it were a cosmic vacuum cleaner, sweeping through space and swallowing everything nearby. But real gravity does not work that way. A black hole is powerful, yes, but it is not hungry, not searching, not reaching across the universe with some special suction. It pulls with gravity in the same basic way any mass pulls. And from far enough away, a black hole can be surprisingly ordinary. If a black hole has the same mass as a star, then at the same distance it does not magically pull harder than that star did. Gravity depends on mass and distance. not on how frightening the object sounds. This is the part that clears the fog. A planet, a star, or a spacecraft can orbit a black hole just as it can orbit any other massive body, as long as it keeps a safe path and does not pass too close. The danger is not that the black hole vacuums everything in. The danger is that near it, gravity changes very quickly over short distances, and paths that once felt stable can become impossible to maintain. Most things in space are not falling straight into black holes, because space is not a room full of objects waiting to be sucked downward. Everything is moving. Stars orbit, gas clouds drift, dust follows curved paths, motion matters. A black hole can only capture what loses enough energy or comes close enough on the wrong path. Otherwise, objects can pass by, swing around, or remain in orbit for immense stretches of time. This is why the cosmic vacuum cleaner image is so misleading. It turns a precise gravitational object into a monster when the real science is quieter and more interesting. Black holes do not break the rules of gravity. They reveal what those rules become under extreme conditions. They are not destructive because they are evil or because they possess some special appetite. They are extreme because a lot of mass has been packed into a very small region, making the surrounding gravitational landscape steep and unforgiving only nearby. And when you understand this, the fear starts to change into clarity. A black hole is not a roaming mouth in the dark. It is a place where gravity is honest, patient, and exact. It does not chase the universe. It simply waits within the paths that physics allows, reminding you that sometimes the most terrifying ideas become calmer when you stop imagining them as myths and begin understanding them as nature. The event horizon, the point of no return. There is a boundary around a black hole that does not look like a wall, does not shine like a warning sign, and yet it may be the most absolute doorway in the universe. This boundary is called the event horizon, and its power comes from a simple but unsettling idea. Once something crosses it, no message, no object, no flash of light can return to the outside world. It is not a solid surface you crash into. If you were falling through a large enough black hole's event horizon, there might be no dramatic line in space, no sudden impact, no visible gate closing behind you. The strange part is that the boundary is defined not by what you feel at that exact moment, but by what is still possible afterward. Outside the event horizon, there are still paths that can lead away. A signal can still escape. A future can still point outward. But inside it, all future directions lean deeper in. It is like passing through a quiet door in the dark and realizing only later that the handle existed on one side only. The event horizon is therefore not a place where matter is destroyed immediately. It is a limit in causality, a border beyond which the universe no longer allows information to come back and tell its story. This is why the name Point of No Return matters. It is not just dramatic language. It means the outside universe has lost access to whatever crossed that line. From far away, an observer may never truly see the crossing happen in an ordinary way, because the light from the falling object becomes stretched, dimmed, and delayed. But for the object falling in, time continues locally, and the journey moves forward. That difference is what makes the event horizon so haunting. It separates experiences. It divides the universe into what can still be shared and what becomes private forever. And perhaps that is why it feels deeper than a scientific boundary. It reminds you that reality is partly made of communication. To exist for the outside world is, in some sense, to be able to send a signal back. The event horizon is where that relationship breaks. Not with noise, not with violence, but with silence. A black hole does not need to announce its threshold. It simply draws a line in space-time where return stops being part of the future. And when you understand that, the event horizon becomes more than an edge around darkness. It becomes a lesson in limits. Some borders are not made of stone, but of possibility itself. Why light cannot escape a black hole. Light is usually the universe's greatest messenger, crossing empty space for billions of years, carrying the color of stars, the memory of galaxies, and the first clues of ancient cosmic events. Yet near a black hole, even this messenger reaches a place where its story can no longer be delivered. The reason is not that a black hole grabs light like a hand, and not that light suddenly becomes weak or tired. Light still moves at the fastest speed nature allows, just as it always does. The problem is deeper and stranger. Near a black hole, the geometry of space-time becomes so extreme that the possible directions light can travel are no longer arranged the way they are around Earth, the Sun, or ordinary stars. In normal space, a beam of light can move outward, sideways, or past an object and continue its journey. It may bend slightly near gravity, but it still has routes that lead away. Close enough to a black hole, those routes change. The paths available to light begin to tilt inward, not because light has chosen the wrong direction, but because outward itself has stopped being a path that leads outside. This is the quiet horror of black hole physics. The fastest thing in the universe does not fail because it is slow. It fails because the road has been rewritten beneath it. Imagine light as a traveler who never rests, who always moves forward, who cannot stand still even for a moment. Around a black hole, that traveler may still rush with perfect speed, but every road ahead curves deeper into the same hidden region. It is like running through a city where every street sign says exit, yet every street has been folded back toward the center. From the outside, this creates darkness, not because the black hole has a surface painted black, but because no returning light reaches your eyes from within that boundary. Seeing depends on light coming back to you. If no light can return, the region becomes visually silent. And this teaches one of the most important truths about seeing the universe. Visibility is not the same as existence. Something can be real, massive, and powerful, yet hidden simply because no signal can escape to announce it. A black hole is therefore not just an object that traps light. It is a lesson in how deeply gravity can reshape the meaning of direction. It tells you that even the speed of light is not absolute freedom. Speed matters, but the shape of space-time matters too. And when that shape becomes extreme enough, even light, the ancient traveler, the cosmic witness, the thing that makes the universe visible, can move forever and still never find its way home. The strange meaning of escape velocity. Escape velocity sounds like a number, but it is really a question the universe asks every moving object. Do you have enough motion to leave this place forever? Or will gravity call you back? On Earth, that question is familiar, even if you have never named it. Throw a stone upward and it slows, stops, and falls, because its speed is not enough to escape Earth's gravity. A rocket is different not because it ignores gravity, but because it carries energy with it, burning fuel as it climbs, pushing higher and faster until Earth's pull becomes less able to bring it home. If a rocket could receive all its speed at once near Earth's surface, it would need to move at about 11 kilometers per second to escape without further help. That is already incredibly fast. Yet Earth is gentle compared with what the universe can build. Make an object more massive, or squeeze the same mass into a smaller space, and escape becomes harder. The surface grows deeper in the gravitational sense, like standing at the bottom of a valley whose walls rise higher and higher around you. A small planet has a shallow valley. Earth has a deeper one. A dense star has a far more demanding one. But a black hole is the extreme case where this idea reaches its breaking point. At its boundary, the speed needed to escape would be the speed of light, and nature does not allow anything with mass to reach that speed. Light itself can only move at that speed, and even that is no longer enough once the boundary is crossed. This is why escape velocity is such a powerful way to understand black holes without turning them into myths. It does not require magic. It does not require a cosmic mouth. It only asks you to follow one simple idea to its most extreme conclusion. Gravity can make leaving harder and harder until leaving is no longer part of the future. And that is the quiet strangeness hidden inside the term. Escape velocity is not just about speed. It is about whether a path outward still exists for you. It teaches that freedom in space is not only about wanting to go somewhere or even moving fast. It depends on the shape of the gravitational landscape around you. Near ordinary worlds, enough energy can carry you away. Near a black hole, beyond the final limit. the price of escape becomes greater than the universe can pay. How massive stars collapse into black holes. Some black holes begin not as darkness, but as enormous stars that spend their lives fighting a quiet war against their own weight. A massive star is born inside a cold cloud of gas and dust, where gravity slowly gathers loose material into a growing center, until the pressure and heat become high enough for nuclear fusion to begin. From that moment, the star starts shining, not because it is burning like wood, but because its core is turning lighter elements into heavier ones and releasing energy. That energy pushes outward, while gravity pulls inward, and for millions of years the star survives through this balance. It is like a giant held upright by its own inner fire. But massive stars live fast. They use their fuel far more quickly than smaller stars, building layer after layer inside themselves, like a cosmic onion. Hydrogen, helium, carbon, oxygen, and eventually heavier elements near the core. Each stage is shorter than the one before it. What once lasted millions of years may later last thousands, then days, then only moments. The star is not simply aging, it is running out of ways to hold itself up. The key turning point comes when the core begins to fill with iron. Iron is different because fusing it does not release useful energy for the star. It does not feed the fire. It ends the support system. Without enough outward pressure from fusion, gravity suddenly wins. The core collapses inward with unbelievable speed, squeezing matter into an extreme state. The outer layers, still falling toward the center, can be blasted outward in a supernova, spreading newly made elements into space. But if the remaining core is massive enough, even the forces that can hold up a neutron star are not enough. Collapse continues. The star's old identity disappears. Its light-filled life, its layers, its storms, its glowing surface. All of it gives way to something far simpler and far stranger. A black hole is born from the failure of a massive star to keep resisting gravity. And in that ending, there is a quiet kind of transformation. The star does not merely die, it leaves behind a region where its gravity becomes its final voice. The same object that once lit the darkness now becomes hidden within it, reminding you that, in the universe, creation and collapse are often part of the same story. The final seconds of a dying star. In the last seconds of a dying massive star, the universe does not roar at first. It becomes suddenly terribly inward. For most of its life, the star has held itself in balance, with pressure from its hot core resisting the pull of its own gravity. But near the end, that balance fails faster than a human mind can comfortably picture. Deep inside, the central material can no longer support the weight above it, and the core begins to collapse almost in free fall. This is not a slow fading, like a candle losing flame. It is more like a cathedral floor giving way beneath a mountain. The outer layers have not yet understood the disaster. Light at the surface may still shine as if the star is alive, while far below, the center is already falling inward at a tremendous speed. In that collapse, atoms are crushed so violently that electrons and protons are forced together, forming neutrons and releasing an enormous flood of neutrinos, ghost-like particles that can pass through matter almost as if the star were transparent. For a brief moment, the core becomes unimaginably dense, and then the falling material rebounds against this newly hardened center. A shockwave forms and races outward, struggling through the star's layers. The details are complex, and scientists still study exactly how that shock gains enough strength in many cases. But the larger truth is clear. The final seconds are not simply destruction. They are a transfer of hidden energy, pressure, gravity, and matter all changing roles at once. What was once a shining sphere becomes a collapsing machine of nature, converting a lifetime of fusion into one last, violent decision. If the remaining core is not too heavy, a neutron star may be left behind. But if too much mass remains, even that dense remnant cannot hold itself up, and the collapse continues toward a black hole. This is what makes the scene so haunting. From the outside, a star may appear to die in fire, but at the center, the deepest event is silence tightening into permanence. The star's final seconds teach you that cosmic endings are not always gradual. Sometimes a life that lasted millions of years turns on a moment too short to breathe, and in that moment, light, matter, and gravity rearrange the future of the universe. Supernova explosions and black hole births. A supernova is the universe speaking in thunder, but the birth of a black hole may happen in the silence left behind. When a massive star reaches the end of its life, its outer layers can be thrown into space with such force that for a time, one dying star may shine brighter than an entire galaxy. This explosion is not just a spectacular ending, it is also one of the great recycling events of the cosmos. Elements forged inside the star are scattered outward, seeding space with material that may one day become new stars, planets, oceans, and living bodies. The calcium in bones, the iron in blood, the oxygen in breath, many of these atoms were shaped by stellar lives and violent deaths long before Earth existed. But at the center of that glowing storm, another story may unfold, one that is almost impossible to see directly. While the outer star erupts outward, the inner core can continue collapsing inward. If the remaining core is heavy enough, there is no stable stopping point. The explosion throws light into the universe, but the center moves toward darkness. This contrast is what makes black hole birth so haunting. The brightest event can leave behind the quietest object. The supernova announces itself across space with radiation, expanding gas and shock waves, while the newborn black hole does not shine from its own surface, does not send a final signal, does not show a face. It is as if the star's last public act is fire, and its private ending is silence. Scientists study these deaths by watching the light curve of supernovae, the chemical fingerprints in the debris, and sometimes the missing remnant that should have been a neutron star but is not visible. In some cases, a star may even collapse with a weaker explosion, or almost no brilliant display at all, quietly fading as its core becomes a black hole. That possibility changes the way you think about cosmic death. Not every ending is loud. Not every transformation announces itself. Sometimes the universe creates its deepest mysteries, not only through violence, but through what remains after the violence passes. A supernova is the scream of a star coming apart. A black hole is the hush that may follow. A dark inheritance left at the center of a vanished sun, reminding you that creation and disappearance can be born in the same breath. Stellar mass black holes. A black hole can be smaller than a city and still carry the weight of several suns. And that single contrast is enough to make the mind slow down. Stellar mass black holes are the smaller members of the black hole family, but small here does not mean gentle or weak. It means compact beyond ordinary imagination. They are called stellar mass because their mass is measured on the scale of stars, often a few times the mass of the sun, sometimes much more, but compressed into a region only tens or hundreds of kilometers across. To compare it calmly, the sun is so large that more than 1 million Earths could fit inside it. Yet a stellar mass black hole may hold many suns worth of mass in a space that could be crossed faster than a plane crosses a country. That is not just heaviness, it is concentration. Gravity becomes intense not only because there is mass, but because that mass has been squeezed into such a small volume that the surrounding region becomes extreme very quickly. This is why stellar mass black holes are so important in astronomy. They are not distant abstract giants hidden only in galaxy centers. They are the more common, personal scale remnants scattered through galaxies, sometimes paired with stars, sometimes drifting unseen through the dark. Many may be quiet, revealing almost nothing unless something nearby betrays them. A companion star moving strangely, hot gas shining in high-energy light, or the faint ripple of space-time when two black holes merge far away. In this way, they teach a different lesson from the enormous black holes at galactic centers. They show that the universe can hide tremendous power inside a surprisingly small boundary. A stellar mass black hole is not large in size, but it is deep in consequence. It reminds you that scale can be deceptive. The biggest looking things are not always the most extreme. and the smallest dark objects can bend the fate of stars around them. Somewhere in the Milky Way, there may be millions of these compact remnants, quiet and invisible unless the universe gives us a clue, and that is what makes them so hauntingly beautiful. They are not vast cosmic monuments, but dense punctuation marks left behind by massive stars, small in diameter, enormous in meaning, silently proving that nature does not need size to create depth. Supermassive black holes at galaxy centers. At the center of many great galaxies, there is a darkness so massive that the whole city of stars seems to arrange its motion around it. These are supermassive black holes, and they are nothing like the smaller remnants left behind by single dying stars. They can contain millions, or even billions of times, the mass of the Sun. Sitting in the dense central regions of galaxies, like a dark heart that does not beat with light, but with gravity. The word heart matters here, because it does not mean the black hole controls every star like a puppet, and it does not mean the galaxy would instantly fall into it. A galaxy is far too vast and complex for that simple picture, but near the center, where stars crowd together and gas moves through a deep gravitational environment, the supermassive black hole becomes one of the most important objects in the entire system. It shapes nearby orbits, influences how gas gathers and heats, and in some galaxies, it powers extraordinary activity when matter falls close enough to release huge amounts of energy before disappearing from view. What makes this so strange is the contrast between size and influence. The black hole itself may be tiny compared with the galaxy, smaller than a grain of dust compared with a continent. Yet its mass can be so concentrated that astronomers can detect it by watching the restless motion of stars and gas around the center. It is not seen like a lamp. It is inferred like a hidden weight beneath a sheet, revealed by the way everything nearby bends and moves. And here, the story becomes deeper. Almost every large galaxy we study seems to have one of these central giants, suggesting that galaxies and their central black holes may have grown together across cosmic time. The galaxy builds stars, gathers gas, merges with other galaxies, and in the middle, the dark heart grows quietly through accretion and collisions, sometimes sleeping, sometimes blazing through its surroundings. It is not merely a destroyer. It is part of the architecture, part of the history, part of the hidden structure that gives a galaxy its central depth. So when you look at a spiral galaxy glowing softly in space, do not only see its beautiful arms and scattered stars. Remember the unseen center, the silent mass around which the innermost motions are written. In the calm darkness of that core, the galaxy keeps one of its oldest secrets, that even light-filled structures may carry a shadow at their heart, and that sometimes the most important presence in a cosmic system is the one that does not shine. Sagittarius A, the black hole in our Milky Way. There is a black hole in our own galaxy, not in some unreachable corner of imagination, but at the very center of the Milky Way you live inside. It is called Sagittarius A star, often written as Sagittarius A, and it sits roughly 27,000 light-years away, hidden behind thick lanes of dust, stars, and glowing gas in the direction of the constellation Sagittarius. What makes it so powerful is not that it threatens Earth, because it does not, and not that it dominates every star in the Milky Way like a ruler holding chains. Its power is quieter than that. Sagittarius A contains about 4 million times the mass of the Sun, yet it occupies a region tiny compared with the vast disk of our galaxy. For a long time, we could not simply point an ordinary telescope at the galactic center and see it clearly, because visible light is blocked by dust between us and the core. So scientists had to learn the galaxy's hidden language. They used infrared telescopes to watch stars near the center move year after year, tracing tight, fast orbits around something they could not see. One star, known as S2, swings around this invisible center with such speed and precision that its motion became one of the strongest pieces of evidence. There must be an enormous compact mass there, and the best explanation is a supermassive black hole. This is what makes Sagittarius A feel personal. It is not just a theory in a textbook, it is the dark anchor of our own stellar island, the quiet center around which billions of stars belong to a larger structure. Your sun is far out in the Milky Way's disk, orbiting the galaxy over hundreds of millions of years, while deep in the middle, Sagittarius A rests like a hidden punctuation mark in the story of our cosmic home. It is usually calm compared with the active black holes that power blazing quasars, but calm does not mean empty. Around it, stars crowd together, gas heats, magnetic fields twist, and space becomes a laboratory for gravity at its most extreme. And perhaps the most haunting part is this. Every night sky you have ever seen belongs to a galaxy with a black hole at its heart. The Milky Way is not just a river of stars above you, it is a vast rotating home with a silent center, reminding you that even the place you come from contains mysteries deep enough to bend the imagination inward. The first image of a black hole. For the first time in human history, we did not simply believe a black hole was there, we saw the shape of its absence. In 2019, scientists with the Event Horizon Telescope released the first image of a black hole, and what made it extraordinary was not that it looked sharp or cinematic, but that it turned one of the universe's most invisible ideas into something human eyes could finally face. The black hole was not in our own galaxy, but in the center of a giant galaxy called Messier 87, far beyond the Milky Way. No single telescope on Earth could have taken that image alone, so observatories across the planet worked together like pieces of one enormous eye, using radio waves and careful timing to create a telescope almost the size of Earth itself. Even then, the image was not a normal photograph in the everyday sense. It was built from huge amounts of data, reconstructed with mathematics, testing, and comparison, until the hidden structure became visible. What appeared was a dark central region surrounded by glowing material, a shadow framed by light. And that is the quiet miracle of the image. The black hole itself was still unseen, because no light comes from inside the boundary, but its presence was revealed by the heated matter and bent radiation around it. Humanity had captured not the object directly, but the effect it carved into the universe. This matters because science often begins with trust in patterns before vision arrives. For decades, black holes were supported by theory, by stellar motion, by energetic signals, by gravitational evidence. But the first image gave people something different, a symbol, a witness, a dark center surrounded by proof. It showed that the strangest predictions of gravity were not just equations on paper or distant intellectual dreams. They described something real enough to leave an image, and perhaps that is why the picture felt so haunting. It was blurry, orange, and imperfect, yet it carried the weight of a threshold crossed. The invisible had not become simple, but it had become present. A thing once hidden behind distance, darkness, and extreme physics had entered human memory. And when you look at that first image, you are not only looking at a black hole, you are looking at the moment our species learned how to see darkness by studying the light it bends around itself. Why the famous black hole image looks like a ring. The famous black hole image looks like a ring because the black hole is not showing you its body. It is showing you how violently it bends the light around it. At first glance, the picture almost looks like a glowing orange donut with a dark center and a bright rim. But that simple shape hides a much deeper truth. The ring is not a solid surface, not a burning edge, and not the outline of the black hole itself. It is light from extremely hot material moving around the black hole, twisted and redirected by gravity before it reaches us. Near a black hole, light does not always travel in the clean straight lines your mind expects. It can curve, loop, and be redirected so strongly that photons from behind the black hole can be bent around toward the observer. In other words, the ring is partly made from light that has taken strange paths through warped space-time, arriving from directions that would normally be hidden. The dark region in the middle is called the black hole's shadow, a visual sign of the place where light paths disappear from view. This is why the image feels so unreal. You are not seeing a normal object. You are seeing the universe distort its own visibility. The brighter part of the ring has a reason too. Some of the glowing gas is moving toward us at enormous speed, and that motion makes its light appear stronger, while material moving away looks dimmer. So the ring is uneven, not because the black hole is lopsided, but because motion, heat, and gravity combine to shape what the telescope receives. This teaches something quietly profound. A black hole can be photographed, not by seeing the darkness directly, but by watching light struggle around it. The ring is the trace of that struggle. It is the universe drawing a border with radiation, motion, and gravity. And when you understand the image this way, it becomes more than a blurry circle. It becomes a map of bent light, a portrait of absence, and a reminder that sometimes the clearest proof of something invisible is the way everything visible curves around it. The shadow of a black hole. A black hole's shadow is not a shadow in the ordinary sense, and that is what makes it so strange. When you see the shadow of a tree on the ground, you are seeing a place where light has been blocked. But the shadow of a black hole is not simply darkness cast onto a surface. There is no wall behind it, no floor receiving its outline, no object sitting in front of a lamp. Instead, the black hole's shadow is the dark shape that appears when light from the surrounding region tries to travel near the black hole, and some of those light paths never make it back to us. It is the visible footprint of an invisible boundary. Around a black hole, light can be bent so strongly that your view becomes distorted, almost as if space itself has become a lens. Some light is redirected toward us, forming a bright surrounding structure, while other light crosses too close and disappears from the outside universe forever. The dark center in the image is therefore not the event horizon itself, but a larger apparent shadow created by the way gravity captures and redirects light. This detail matters, because it means the shadow is a kind of cosmic evidence. We are not seeing the black hole directly, we are seeing the place where seeing fails. And from that failure, scientists can learn something real. The size and shape of the shadow can reveal whether the black hole behaves as Einstein's theory predicts. If the shadow were wildly different from expectation, it would suggest that our understanding of gravity near extreme objects is incomplete. But the images we have so far match the broad predictions remarkably well, giving us a rare test of physics in a place no spacecraft could ever visit. The shadow also teaches a quieter lesson about perception. Sometimes the most important thing in an image is not the light, but the absence the light surrounds. The black hole does not pose for the universe. It leaves a negative signature, a dark silence carved into brightness. And when you look at that shadow, you are looking at more than darkness. You are looking at the limit of returned information, the edge of what the outside universe can still report, and a reminder that even the unseen can leave a shape precise enough for science to measure. Accretion disks, the glowing matter around black holes. The brightest thing near a black hole is often not the black hole at all, but the matter that has not yet crossed the final boundary. This glowing structure is called an accretion disk, and it forms when gas, dust, or torn stellar material falls toward a black hole while still carrying sideways motion. Instead of dropping straight in, the material begins to whirl around, flattening into a disk, like water circling a drain, but on a scale so extreme that the comparison quickly breaks down. The black hole itself remains dark, because no light escapes from within its hidden region, but the matter around it can become violently luminous before it disappears. As the gas spirals inward, different layers move at different speeds. They rub, collide, twist through magnetic fields, and heat up to enormous temperatures. This heating makes the disk shine, sometimes in visible light, sometimes in ultraviolet light, and often in high-energy radiation that human eyes could never see. The important point is that the light comes from the journey, not the destination. Matter is not glowing because it is already inside the black hole. It is glowing because it is still outside, losing energy, tightening its orbit, and converting motion into heat. In this way, an accretion disk becomes a kind of cosmic warning lamp, not placed there by intention, but created naturally by physics. It reveals the black hole by refusing to vanish quietly, and there is something deeply strange in that contrast. The center gives nothing back. Yet the surroundings can blaze with more intensity than ordinary stars. Darkness in this case is not isolated from light. It is framed by it. The accretion disk teaches you that the universe often reveals hidden things through their edges, through the last bright activity before silence. A black hole may be invisible by itself, but the matter around it tells a story of speed, heat, pressure, and surrender. And when you picture that glowing disk, you are not looking at simple destruction. You are looking at matter writing its final message in light before crossing into a place where messages no longer return. Why black holes can be brighter than galaxies? The darkest object in the universe can become the engine behind one of the brightest lights the universe has ever produced. And that contradiction is where the real story begins. A black hole itself does not shine, because anything already beyond its point of no return cannot send light back to space. Yet the region just outside an active black hole can release an astonishing amount of energy. The key is not darkness, but efficiency. When matter falls toward a compact, massive object, it does not simply disappear. Before it is lost, its motion can be transformed into heat and radiation with extraordinary power. In ordinary stars, light comes from nuclear fusion in the core, a slow and steady process where atoms combine and release energy over millions or billions of years. Near an actively feeding supermassive black hole, the energy source is different. Gas is pulled into a fierce central environment, squeezed, accelerated, heated, and forced to give up a large fraction of its gravitational energy before crossing the final limit. That process can be so efficient that a region smaller than a solar system may outshine hundreds of billions of stars spread across an entire galaxy. This is why some galactic centers, called active galactic nuclei, can appear brighter than the galaxies around them. The black hole is not glowing like a star. It is making nearby matter pay an enormous energy price on the way inward. And the smaller the region where that energy is released, the more intense the light can become. This is not true for every black hole. Many are quiet, surrounded by too little material to produce a grand display. But when a supermassive black hole has enough gas nearby, it becomes a cosmic power station, turning falling matter into radiation so bright it can travel across the visible universe. The lesson is subtle. Darkness and brightness are not always enemies. Sometimes the deepest darkness creates the conditions for the most violent illumination around it. A black hole can remain invisible at its center, while making its surroundings visible across billions of light years, reminding you that the universe often hides its strongest engines behind the very light they create. Quasars, ancient beacons powered by black holes. Some of the oldest light reaching Earth does not come from ordinary stars, but from cosmic beacons powered by black holes when the universe was still young. These beacons are called quasars, and at first they confused astronomers because they looked almost like stars through early telescopes, small and point-like. Yet their light carried a strange message. They were not nearby stars at all, but incredibly distant galactic centers shining across billions of light years. A quasar is not a black hole shining by itself. It is the brilliant region around a supermassive black hole that is actively drawing in huge amounts of gas. As that material crowds into the central region of a young galaxy, it becomes extremely hot and releases light so intense that the quasar can be seen from across the observable universe. This makes quasars more than bright objects. They are time machines made of light. When we observe a distant quasar, we are not seeing it as it is today. We are seeing it as it was billions of years ago, because its light has traveled through expanding space for an almost unimaginable length of time before finally reaching our telescopes. In that sense, quasars are messages from the early universe, written in radiation instead of ink. They tell us that enormous black holes already existed when galaxies were still forming and changing rapidly, which raises one of the deepest questions in modern astronomy. How did some black holes grow so large so early? Quasars also help scientists study the space between galaxies. Because their light passes through clouds of gas on its journey to us, carrying fingerprints of everything it crossed. A single quasar can act like a lamp behind a cosmic fog, revealing invisible material between here and the distant past. And this is where the image becomes quietly beautiful. A quasar is a lighthouse, but not one built on a shore. It is powered by gravity, surrounded by a young galaxy, and shining from an age before Earth, before the sun, before anything human had begun. Its light arrives late, like a letter from a vanished empire. And when you receive it, you are reminded that the universe does not only show you where things are, sometimes it shows you when they were. Jets shooting from black holes. The phrase, "nothing can escape a black hole," is true only after the final boundary has been crossed, and that small detail changes the entire picture. When you see images or illustrations of black holes launching enormous jets into space, it can seem like a contradiction, almost as if the black hole is swallowing matter and then spitting some of it back out. But the jets do not come from inside the black hole. Nothing that has crossed the event horizon comes back to form them. Instead, these jets are born in the furious environment just outside it, where gas, plasma, magnetic fields, and rotation become locked into one of the most powerful natural engines in the cosmos. As matter spirals around the black hole, it becomes extremely hot and electrically charged, which means magnetic fields can grip and guide it. Around many active black holes, especially spinning ones, these magnetic fields can become twisted and stretched into narrow channels above and below the black hole's poles. Some of the surrounding material is then accelerated outward along those channels at nearly the speed of light, forming jets that can travel thousands or even millions of light years into space. So the black hole is not breaking its own rule. The rule applies to what goes too far in. The jets are made from matter and energy that remain outside, caught in the chaos before crossing the point of no return. This is what makes them so fascinating. They are not escapes from the black hole's interior, but near misses turned into cosmic beams. And they are not gentle streams. They can carry enough energy to affect whole galaxies, heating gas, disturbing star formation, and carving huge bubbles into surrounding space. In a strange way, the black hole's darkness helps organize one of the universe's most dramatic displays of motion. The center stays silent, but its surroundings become a launching ground. And once you understand that, the contradiction becomes a lesson. Nature often hides its power not in the thing itself, but in the boundary around it, where falling inward and being flung outward can happen side by side without ever violating the deeper rules of reality. How black holes shape their galaxies. A galaxy is not shaped only by its stars. Sometimes its deepest structure is influenced by a darkness at the center that almost never touches the stars directly. This is the surprising role of a supermassive black hole. Not simply a destroyer, not a cosmic beast tearing a galaxy apart, but a hidden part of the galaxy's architecture. Its gravity strongly rules only the central region, and it does not pull every distant star like a hand controlling a machine. Most stars in a galaxy move under the combined gravity of all the stars, gas, dark matter, and the whole galactic system. But the central black hole can still shape the galaxy in a more subtle and powerful way. Through the gas that flows toward the center, the energy released around it, and the way that energy changes the future of star formation. Galaxies need cold gas to make new stars. If gas cools and gathers, it can collapse into stellar nurseries. But when a central black hole becomes active, the region around it can release enormous energy into surrounding space, heating gas, stirring it, or pushing it away from the central regions. This does not mean the black hole is simply destroying the galaxy. In many cases, it may be regulating it, like a dark thermostat in the core, preventing too much gas from cooling too quickly. Astronomers have found that the mass of a central black hole often relates to the properties of the galaxy's central bulge, suggesting that black holes and galaxies grow through connected histories. They may feed from the same cosmic supply, respond to the same mergers, and influence each other across immense time. This is what makes the idea so beautiful. A black hole can be tiny compared with the galaxy around it, yet still participate in the galaxy's long-term rhythm. It is not the whole architect, but it can affect the blueprint. It can help decide when the galaxy glows with new stars, when it calms, when it becomes restless, and when its central engine falls quiet again. So when you look at a galaxy, do not imagine it as only a collection of lights. Imagine it as a living structure of motion, gas, gravity, and memory, with a silent center that may help shape its fate without ever needing to shine. The quiet black holes we cannot see. Not every black hole announces itself with fire. Many may be resting in the dark so quietly that the galaxy moves around them without ever revealing their name. These are quiet black holes, and they may be among the most common black holes in the universe, not because they are weak, but because they have nothing nearby to make them shine. A black hole does not glow on its own like a star, and if no gas is falling toward it, no bright disk forms, no powerful radiation flares, and no dramatic signal rises into space. It can simply exist, cold to our telescopes, silent in ordinary light, carrying its mass without a visible face. This is why the idea of an inactive black hole is so different from the frightening image people often carry. It is not an invisible predator roaming with intention. It is more like a sleeping remnant, a dense gravitational presence left behind after a massive star's life has ended, drifting through the galaxy unless something comes close enough to interact with it. Around it, space may be calm, no storm of glowing matter, no violent beam, no cosmic alarm, just an object whose presence is hidden because the universe has given it no material to light up. Astronomers think many stellar mass black holes could be this quiet, scattered through galaxies like extinguished lanterns whose weight remains even after their flame is gone. They are difficult to find because science often depends on signals, and silence gives almost nothing away. A black hole surrounded by emptiness is not easy to separate from darkness itself. And yet, this quietness is not emptiness. It is a lesson in how much of reality may exist without performance, without brightness, without spectacle. The universe is not only made of things that shine for us. Some of its deepest objects are patient, unseen, waiting not in hunger but in stillness. A quiet black hole reminds you that invisibility does not mean absence, and that sometimes the most powerful things in nature are not the ones making noise, but the ones whose silence is almost complete. How scientists detect invisible black holes. A black hole is like a suspect that never appears at the crime scene, yet leaves fingerprints on everything around it. Scientists cannot usually detect a quiet black hole by simply seeing it, because the black hole itself sends no ordinary light back to our telescopes. So astronomy becomes a kind of cosmic detective work, built not on the object's face, but on the clues it leaves behind. The first clue is motion. If a visible star moves as if it is orbiting something massive, but no bright companion can be seen, scientists begin to ask what hidden object could be pulling it. The answer is not guessed casually. They estimate the unseen mass from the star's motion, then compare it with what normal objects can be. If the hidden mass is too large and too compact to be a faint star, a white dwarf, or a neutron star, a black hole becomes the strongest explanation. Another clue comes from material nearby. Gas falling toward a compact object can heat up and release high-energy radiation before it disappears. So telescopes that see beyond human vision can reveal places where invisible gravity is doing visible work. A third clue comes from gravity itself. When two black holes merge, they can shake space-time and send out gravitational waves, tiny stretching and squeezing signals that detectors on Earth can measure. In that case, scientists are not seeing light from the black holes at all. They are listening to the shape of space-time change. This is what makes black hole detection so elegant. It proves that seeing is not the only way to know. A thing can be real because of the way it moves other things, heats its surroundings, bends paths, or leaves a signal in the fabric of the universe. The black hole stays hidden, but the universe around it testifies. And in that quiet testimony, science does something almost poetic. It finds the invisible not by forcing it to shine, but by learning to read the shadows, motions, and whispers it leaves behind. Stars orbiting an invisible center. A black hole in a binary system is not alone in the dark. It is locked in a gravitational dance with another object, and the dance itself becomes the clue. A binary system simply means two objects bound together by gravity, circling a shared center of mass, rather than one object perfectly sitting still while the other moves around it. That detail matters because it changes the image in your mind. A black hole in a binary is not always a lonely remnant drifting through space. It can be partnered with a normal star, a neutron star, or even another black hole, each one tugging on the other in a rhythm written by gravity. If the companion is a visible star, astronomers can watch that star sway, speed up, slow down, and trace an orbit around something they cannot see. The black hole may remain invisible, but the partner's motion reveals the hidden weight in the system, like a dancer moving around someone standing in shadow. In some binaries, the two objects are widely separated and move calmly for long ages, each holding its distance in a stable orbital pattern. In others, they are close enough that their motions become faster, more intense, and more revealing. What makes binary black holes especially powerful is that they show gravity not as a simple downward pull, but as a relationship. Each object responds to the other. Each orbit carries information about mass, distance, and history. And over immense time, some compact pairs can slowly lose orbital energy, drawing closer until their final interaction becomes one of the most dramatic events in modern astronomy. But even before that ending, the binary itself teaches a quiet truth. Black holes are not just isolated darkness. They can be partners in cosmic choreography, shaping and being shaped by another object's motion. In a universe that often feels empty, a binary system reminds you that even the darkest bodies can belong to a pattern, and that sometimes the only way to understand what cannot be seen is to watch what moves beside it. When a black hole steals matter from a star. A black hole does not steal from a star like a creature feeding in the dark. The transfer begins much more quietly, as a problem of closeness, motion, and gravity. In a binary system, a normal star and a black hole can orbit each other for millions of years, each moving around their shared gravitational balance point. If the star stays far enough away, it can continue living almost normally, holding its gas in place with its own gravity. But if the orbit is tight, or if the star expands as it ages, its outer layers can reach a limit where the black hole's gravity begins to matter more strongly. Astronomers call this region the star's Roche lobe, which you can think of as the invisible gravitational space where a star can safely keep its material. Once the star grows beyond that boundary, gas from its outer atmosphere can spill through a delicate balance point between the two objects and begin flowing toward the black hole. Nothing supernatural is happening. The black hole is not reaching out with intention. The star has simply expanded into a place where the rules of gravity no longer let all of its matter remain loyal to it. The stream of gas does not usually fall straight in because it carries the sideways motion of the orbit. Instead, it curves, wraps, and gathers into a rotating flow around the black hole, gradually losing energy as it moves inward. In other cases, the black hole may capture part of a strong stellar wind, especially from a large hot companion star shedding material into space. These are two different ways matter can transfer. One like an overflowing atmosphere, the other like catching gas from a cosmic breeze. What makes this so fascinating is that the process reveals how fragile a star's outer layers can become when gravity is shared between two bodies. A star may look whole from far away, but in a close binary, its edge is not simply a surface. It is a negotiation. It depends on mass, distance, orbit, and time. Slowly, the black hole can gain material, while the companion star loses part of itself, changing both objects' futures. And in that exchange, the universe teaches a calm but unsettling lesson. Destruction does not always arrive as violence. Sometimes it begins as a slow imbalance, a quiet crossing of an invisible line, where matter follows the path gravity has opened and a star, little by little, gives part of its light-filled body to the dark. X-rays from black hole neighborhoods. The universe has more languages than your eyes were built to read, and around black holes, one of the clearest languages is X-rays. Human vision catches only a narrow strip of light, the familiar glow of stars, fire, and reflected sunlight, but black hole neighborhoods often speak in far more energetic signals. X-rays are a form of light too, just beyond what your eyes can see, carrying much more energy than visible light. They appear when matter near a black hole is heated to extreme temperatures, especially in the inner regions where gas moves violently, magnetic fields twist, and particles are accelerated into chaotic motion. This does not mean the black hole itself is glowing. It means the space around it has become so energetic that ordinary light is no longer enough to tell the story. The material there can become millions of degrees hot, and at those temperatures, it releases radiation that belongs to a harsher, more hidden part of the spectrum. To detect it, scientists cannot simply use normal telescopes from the ground, because Earth's atmosphere blocks most cosmic X-rays before they reach us. That protection is good for life, but it also means we need space telescopes to listen properly. Instruments above the atmosphere, such as X-ray observatories, can reveal black hole systems that would otherwise look quiet or completely invisible. Through X-rays, astronomers can study how fast material changes, how compact the source must be, and how extreme the environment is near the unseen center. A sudden flicker in X-rays can reveal activity happening in a region smaller than a star, while repeated patterns can hint at motion close to the black hole. This is why X-rays feel like another grammar of the cosmos. Visible light may show you the calm face of the sky, but X-rays reveal the hidden tension beneath it. Hot gas, violent acceleration, and gravity turning motion into radiation. And when you understand that, the dark neighborhood of a black hole stops being silent. It becomes a place speaking in invisible light, waiting for us to build the right eyes to understand it. Spaghettification, when gravity stretches matter. Spaghettification sounds almost playful, but it describes one of the most unforgiving ways gravity can reveal that your body is not a single point, but a long object stretched through space. The idea is simple once you slow it down. When you fall near something extremely compact, the part of you closer to it feels a stronger pull than the part farther away. If your feet are pointed toward the black hole, your feet are being pulled more strongly than your head. On Earth, this difference is far too small for you to notice in daily life. Gravity pulls you downward, but it does not noticeably stretch you because Earth is large, and the difference between the gravity at your feet and at your head is tiny. Near a black hole, especially a smaller stellar mass black hole, that difference can become enormous over the length of a human body. Your feet would be accelerated inward faster than your head, and that unequal pull would stretch you lengthwise. At the same time, matter can be squeezed from the sides because gravity is not just pulling in one simple direction. It is changing across space. This is what scientists call spaghettification. Not a cartoonish transformation, but the physical result of gravity varying so sharply from one point to another that ordinary structures cannot hold themselves together. The bones, cells, and atoms that usually remain arranged as you would no longer be able to resist the difference in pull across your body. The important lesson is that danger near a black hole is not only about how strong gravity is in total. It is about how quickly gravity changes over distance. A very large black hole can have a surprisingly gentle event horizon because its gravity changes more gradually at that boundary, while a smaller black hole can produce deadly stretching far earlier. That fact is strange because it means size changes the experience of falling. The same word black hole can hide very different physical environments. Spaghettification teaches you that gravity is not always felt as simple weight. Sometimes it becomes tension. Sometimes it becomes a gradient, a difference between one part of a thing and another. And in that difference, the illusion of being solid and whole begins to fail. You are held together by forces inside matter, but near enough to an extreme compact object gravity can ask a harsher question than anything on Earth ever asks. Can all parts of you continue moving together? When the answer becomes no, stretching is not a metaphor anymore. It is the universe showing that even a body, even a star, even a cloud of gas is only whole, while the surrounding gravity allows it to remain whole. Tidal forces near a black hole. Every ocean tide on Earth is a small, gentle clue to a force that becomes almost unthinkable near a black hole. When the moon pulls on Earth, it does not pull every part of our planet with exactly the same strength. The side of Earth facing the moon feels a slightly stronger pull. The far side feels a slightly different pull, and this difference helps raise the oceans into tides. Nothing dramatic happens to the planet because the difference is modest, spread across a large world, and Earth is strong enough to remain whole. But this same principle, taken to an extreme, becomes one of the most important dangers near a black hole. Tidal forces are not simply gravity itself. They are the unevenness of gravity across an object. A planet, a moon, a gas cloud, or a star can survive ordinary gravity if all parts of it are pulled almost equally. The trouble begins when one side is pulled much harder than the other. Near a black hole, especially a compact one, the difference between the near side and the far side of an object can become enormous. A star passing too close may find that its near edge is being drawn inward more strongly than its far edge can follow, while its own internal gravity tries to hold it together. If the tidal force wins, the star can be distorted, stretched, and in extreme cases torn apart into streams of gas. This is not because the black hole is attacking it like a beast, but because the star has entered a region where gravity changes too sharply from one side to the other. The moon gives Earth tides measured in ocean movement. A black hole can create tides powerful enough to rewrite the shape of matter itself. And this reveals a deeper lesson. In space, danger is often hidden not in how strong a force feels at one point, but in how differently that force acts across a whole body. Stability depends on togetherness. A world remains a world because its parts can keep moving as one. But near a black hole, gravity may stop treating an object as one thing and begin separating it into near side and far side, inner edge and outer edge, past form and future debris. The quiet rise and fall of Earth's seas is therefore connected to the most extreme destruction in the cosmos by the same idea. A tide on Earth is a rhythm. Near a black hole, a tide can become a verdict. Could you survive falling into a giant black hole? The most surprising thing about falling into a giant black hole is that the moment everyone fears most might not feel like a moment at all. For a small black hole, the tidal forces near the boundary can be so severe that an astronaut would be stretched apart long before reaching the deepest regions. But for a truly enormous supermassive black hole, the situation changes in a strange and counterintuitive way. Because the black hole is so large, the gravity at its event horizon can change more gradually across the length of your body. That means, in theory, if you cross the event horizon of a giant black hole, you might not instantly feel anything dramatic. No fiery wall is guaranteed by standard general relativity, no sudden impact, no visible line painted across space. You could pass the point of no return without your local sensors announcing it. Your heart could still beat, your watch could still tick, a small object beside you could still float nearby for a while. From your own perspective, physics around you might continue normally in that immediate moment, but the calm would be deeply misleading because survival is not the same as escape. Once inside, every possible future path leads deeper inward. Even if the crossing itself feels gentle, the danger has changed form. It is not a door that burns you when you touch it. It is a door that quietly removes every route back. Farther in, the tidal forces would eventually grow stronger, and no body, spacecraft, or known material could remain intact forever. The larger the black hole, the more time you might have after crossing before the environment becomes fatal. But the ending is not avoided, only delayed. This is what makes the idea so unsettling. A giant black hole can be deadliest not because it is immediately violent, but because it can make the irreversible feel ordinary. It teaches you that the universe does not always mark its most important boundaries with sensation. Sometimes the greatest change in your fate can happen quietly, while everything around you still seems calm. And perhaps that is the most haunting lesson of falling into a giant black hole. You might cross the line that separates return from no return without noticing the line itself, carrying your normal thoughts forward into a future that has already closed behind you. What you would see while falling in. The view near a black hole would not look like falling into a simple dark hole. It would look like the sky itself losing its ordinary shape. From the perspective of a falling observer, the most dramatic change would come from light being bent, concentrated, and redirected by extreme gravity. Stars behind the black hole would not simply disappear in a clean circle. Their light could curve around the black hole, producing warped arcs, duplicated images, and strange rings of brightness where the same region of space appears in more than one place. If there were a glowing disk of hot gas around the black hole, the scene would become even more surreal. Parts of the disk behind the black hole could be lifted into view by gravitational lensing, so the observer might see the front, the sides, and even distorted light from the far side at once, as if space had folded the image upward. Motion would also change the picture. As the falling observer accelerates, light from the direction of travel can become intensified and shifted toward higher energies, while light from behind may fade and redden, depending on the path and speed. The outside universe would not appear like a normal night sky anymore. It would be squeezed, stretched, and rearranged by both gravity and motion, turning familiar stars into a distorted map of where light has struggled to travel. But this is not a magical vision of another universe, and it is not a guaranteed window into the future. What is seen depends on the black hole's size, spin, surrounding matter, and the observer's path. Near a quiet black hole, the view may be mostly warped starlight and deep darkness. Near an active one, it could be dangerously bright with radiation from hot gas outside. The important truth is that the black hole changes vision by changing the roads light can take. It does not create fantasy, it edits visibility through gravity, and that is what makes the scene so haunting. Falling in would not only be a journey through space, but through a place where seeing itself becomes unstable, where the universe still sends light, but no longer sends it in the simple directions the mind expects. Why time slows near a black hole? Place two perfect clocks in the universe, one far from a black hole and one hovering much closer to it. And the strange truth is that they will not agree on how much time has passed. This is not because one clock is broken, and not because time only feels slower to someone near extreme gravity. In Einstein's picture, time is part of the structure of the universe, and gravity can change how that structure behaves. Near a massive object, time runs more slowly compared with time far away. On Earth, this effect is real but tiny. Clocks closer to Earth's surface tick a little more slowly than clocks higher above it, because the lower clock sits deeper in Earth's gravity. We even have to account for effects like this in precise technology, including satellite systems, because time is not perfectly universal. Near a black hole, the same idea becomes far more dramatic. A clock placed close to the black hole would tick more slowly when compared with a clock far away in weaker gravity. If the close clock could send signals outward, those signals would arrive increasingly delayed and stretched, as if the clock were fading into a slower rhythm from the distant point of view. But locally, beside that close clock, nothing would seem strange. It would still tick 1 second at a time. A heartbeat would still feel normal. A thought would still unfold in its own natural pace. The difference only appears when two regions compare their time with each other. That is the quiet shock. Time is personal to the path you take through gravity. It is not one cosmic river flowing at the same speed everywhere. It is more like a fabric whose rhythm changes depending on where you stand. A black hole does not simply pull on matter. It changes the rate at which moments are measured near it. Two clocks can both be honest and still age differently. And once you understand that, time stops feeling like a background and begins to feel like part of the landscape itself. Near a black hole, The question is not only where you are, but how quickly your future is unfolding compared with someone far away. The universe, in its deepest gravity, does not give every observer the same tempo. It lets one clock move gently onward, while another far away races ahead into years the first has barely lived. Gravitational time dilation. Einstein's strangest lesson about gravity is not that it bends the path of planets, but that it can stretch the pace of time itself. Gravitational time dilation means that time does not flow at one perfect universal speed everywhere in the cosmos. It changes depending on how deep you are inside a gravitational field. Far from massive objects, time runs a little more freely. Close to something very massive, time runs more slowly when compared with a distant region. This sounds impossible at first because everyday life trains you to think of time as the one thing everyone shares equally, like an invisible background music playing at the same tempo for all observers. But Einstein's general relativity changed that picture. Space and time are not separate stages where gravity happens. They are part of one connected structure, and mass changes that structure. A planet bends it gently. A star bends it more strongly. A black hole bends it so extremely that the stretching of time becomes one of its defining features. You do not need equations to feel the idea. Think of time as a road that can become longer or shorter depending on the landscape. In weak gravity, moments are spaced in one way. In strong gravity, those same moments are stretched differently when judged from far away. Locally, nothing feels broken. A person near strong gravity would not feel their own thoughts slowing down because everything around them, heartbeat, breathing, chemistry, movement, belongs to the same local rhythm. The strangeness appears only when that rhythm is compared with another place. This is why gravitational time dilation is not an illusion or a trick of perception. It is a measurable feature of reality. Extremely precise clocks have shown that height, motion, and gravity affect the passage of time, even here near Earth, though the effect is tiny. Near a black hole, the same principle becomes enormous enough to feel almost philosophical. Time becomes less like a ruler and more like a landscape you can move through at different depths. The deeper you go into gravity, the more your path through time differs from someone watching from far away. And this changes the way you understand existence. The universe does not hand every location the same present moment in the same way. What you call now is partly shaped by where you are, how you move, and how strongly gravity curves the world around you. Near a black hole, time is not destroyed. It is stretched into something unfamiliar, something that reminds you that even the flow of moments is not above nature's laws. The deepest gravity does not only pull on matter, it pulls on the meaning of time, quietly revealing that the future is not paced equally for everything under the stars. How a distant observer sees you near the horizon. The same fall into a black hole can become two different stories depending on who is watching. From far away, a distant observer does not see the falling traveler simply rush through the event horizon and vanish in an ordinary instant. Instead, the signals coming from the falling object arrive more and more slowly, as if each moment is being stretched before it can escape to the outside. A flash of light sent once every second near the black hole would not keep arriving once every second to the distant observer. The flashes would come later, weaker, and shifted toward redder wavelengths until the falling object seemed to fade toward darkness. In this outside view, the traveler appears to slow down near the horizon, becoming dimmer and dimmer, almost frozen at the edge. But this is not what the falling traveler experiences locally. For the person falling inward, their own clock continues normally. Their thoughts do not freeze. Their heartbeat does not wait for the outside universe to catch up. They cross the horizon in a finite amount of their own time, even though the distant observer never receives a clean final image of that crossing. This is the strange split that black holes create. Not a contradiction, but two valid perspectives shaped by gravity and the travel of light. The outside observer is limited by what signals can reach them. The falling observer is carried along their own path through space-time. One story is made from delayed fading information. The other is made from direct local experience, and this teaches something deeper than a visual trick. In extreme gravity, reality is not always a single shared picture. What happens can be simple for one observer and unreachable for another. The black hole does not merely hide objects. It separates viewpoints. It turns the act of seeing into a matter of position, gravity, and time. And near the horizon, the universe seems to whisper a quiet lesson. What is real to one path may become forever unfinished to another. Redshift. Light losing energy while escaping gravity. The color of light can become a quiet confession, and near a black hole, that confession slowly turns red. When light tries to climb away from a powerful gravitational field, it does not lose its identity as light, and it does not slow down in empty space the way a tired object might. Light always travels at the speed nature allows locally, but to a distant observer, the light escaping from deep gravity arrives with less energy than it had when it began its journey. That loss shows up as a stretching of its wavelength, and stretched light shifts toward the red end of the spectrum. This is called gravitational redshift. You can picture it gently. A photon leaves a region close to a black hole like a small messenger carrying a note uphill through an invisible landscape. The climb costs energy. By the time that message reaches someone far away, it is still a message, but its tone has changed. Its color has softened downward. Blue light may become less blue. Visible light may drift redder. Light that was already red may be stretched beyond what human eyes can see. This is not the same as ordinary dimming, where light only spreads out with distance. Redshift changes the light's energy itself as measured far away. It is one of the ways gravity leaves fingerprints on radiation without touching it like a hand. Around black holes, the effect can become extreme. Light emitted from gas very close to the black hole can arrive redder than expected, and signals from objects nearing the horizon can become increasingly stretched and faint. To the outside universe, the escaping light is not just delayed, it is drained into longer, weaker waves, as if gravity has lowered the pitch of the cosmos. Astronomers use this idea to study compact objects, because the color and energy of light can reveal how deep in gravity it was produced. A spectrum becomes more than a rainbow. It becomes a map of struggle, and this is where the science becomes strangely reflective. Light is the thing we trust to show us reality, yet even light carries the memory of the path it survived. Near a black hole, color is not merely beauty. It is evidence. It tells you that the universe is not a flat stage where signals travel unchanged, but a shaped place where gravity can stretch a message before it reaches you. Redshift is the fading blush of light escaping a deep gravitational well, a calm visual proof that even the fastest messenger in nature can arrive altered by the darkness it climbed away from, the photon sphere, where light can orbit. There is a place near a black hole where light can, in theory, run in a circle, as if the fastest thing in the universe has been trapped on a track made from gravity itself. This strange region is called the photon sphere, and it is not a surface, not a shell of material, and not a glowing layer you could touch. It is a special distance from a non-rotating black hole where the curvature of space-time is so extreme that light moving in just the right direction could orbit the black hole instead of immediately escaping outward or falling inward. The idea feels almost impossible because light normally seems like pure motion, always crossing space, always delivering images from one place to another. But near a black hole, space is curved so deeply that motion itself can bend into a loop. A photon, which is a particle of light, does not decide to orbit. It simply follows the path that space-time gives it. And at the photon sphere, that path can become circular. But this orbit is not peaceful or stable like the moon around Earth. It is balanced on a knife edge. If the photon is shifted even slightly outward, it may spiral away and escape into space. If it is shifted slightly inward, it may fall toward the black hole and never return. This makes the photon sphere less like a safe road and more like a perfect circular ridge on the side of a bottomless valley, possible to follow only under impossibly exact conditions, and lost the moment the path is disturbed. The photon sphere helps explain why black holes can produce such strange visual effects, because light passing near this region may loop partway around the black hole before reaching an observer. Some light can even take more than one partial trip around before escaping, carrying a distorted message from directions that would normally remain hidden. In a sense, the photon sphere is where vision becomes delayed, multiplied, and curved into something unfamiliar. It is not where light rests, because light never rests. It is where light's forward motion can be bent so strongly that forward becomes circular. And that is the quiet wonder of it. The universe has places where even a straight traveler can be made to draw a ring. The photon sphere reminds you that speed alone does not guarantee freedom. Even light, moving as fast as anything can move, must obey the shape of the world it moves through. Near a black hole, that shape becomes so extreme that the path of light can briefly resemble a thought caught in repetition, circling the darkness before either escaping with a warped story or disappearing into silence. The innermost stable, circular orbit. There is a last safe circle around a black hole, a final orbit where matter can still keep going around, instead of being forced into a one-way fall. Scientists call it the innermost stable circular orbit, but the idea is calmer than the name sounds. Around Earth, a satellite can orbit at many distances if it has the right speed, and if its path is nudged a little, it can often settle into a nearby orbit. Around a black hole, the rules become less forgiving. Far enough away, gas, dust, or a spacecraft could circle in a stable path, held by the balance between its forward motion and gravity's inward pull. But move too close, and circular motion stops being safely sustainable. There comes a boundary for matter where the orbit is no longer stable. A tiny disturbance inward does not simply create a slightly lower orbit. It can begin an irreversible plunge. This is why the innermost stable circular orbit is like the last ledge on a mountain before the slope becomes too steep to stand on. It is not the event horizon, and it is not a physical surface. It lies outside the black hole, marking the closest region where ordinary matter can keep circling in a lasting way. Inside it, matter may still whirl for a moment, but it is no longer in a stable orbit. Its path becomes a fall disguised as rotation. This matters because the inner edge of a glowing disk around a black hole is often shaped by this limit. Material can orbit, heat, and radiate outside the last stable orbit, but once it passes inward, it is effectively committed to descending toward the black hole. The exact location of this last safe orbit depends on the black hole, especially whether it is spinning and which direction the matter is moving. Around a rotating black hole, matter orbiting with the spin may remain stable closer in, while matter moving against the spin has a more distant last safe orbit. That one detail turns the orbit into a measuring tool. By studying radiation from the inner disk, scientists can learn something about the black hole's spin and the extreme environment near it. The deeper lesson is that space near a black hole is not divided only into outside and inside. There are layers of possibility. Regions where motion is free, regions where motion is fragile, and regions where the future has already begun to tilt inward. The innermost stable circular orbit is one of those quiet thresholds. It tells you that falling into a black hole does not always begin with crossing the final boundary. Sometimes it begins earlier, at the moment when a path stops being a path and becomes a surrender. Black hole spin. A black hole is not only heavy, it can also spin, and that spin turns it from a silent weight into something closer to a rotating storm in space-time. This matters because most things in the universe rotate. Stars rotate, gas clouds rotate, galaxies rotate. Even when a massive star collapses, the motion it already had does not simply vanish. Like an ice skater pulling in their arms and spinning faster, collapsing matter can concentrate its rotation as it shrinks inward. So a black hole is rarely just a still, simple gravitational object. It often carries spin as part of its identity, and that spin changes the space around it in ways that are far stranger than the rotation of a planet. When Earth spins, its solid surface turns through space. When a black hole spins, there is no ordinary surface turning like a ball. Instead, the surrounding space-time itself is affected by the rotation, as if the geometry near the black hole has been stirred. This is why it can help to picture a black hole not as a dark marble, but as a deep, rotating whirlpool, where the water is not water at all, but the structure of space and time. Matter nearby does not simply feel gravity pulling inward. It also encounters a rotating environment where paths can be twisted, where motion in one direction may be easier than motion in another, and where the history of how the black hole formed still echoes in its spin. A black hole can spin because it inherited angular motion from the star that made it, from material that later fell toward it, or from mergers with other compact objects. And scientists care about that spin because it reveals something about the black hole's past. A slowly spinning black hole may have grown differently from one spinning extremely fast. A fast spin can suggest long periods of feeding from material moving in a consistent direction, while chaotic growth or collisions can leave a more complicated signature. Spin also affects how much energy can be released by matter near the black hole, because rotating spacetime changes how close material can move before its final descent. This does not mean the black hole is alive, or choosing, or behaving like a machine with gears. It means motion has become part of gravity's shape. The black hole is not merely sitting in the universe. It is rotating within the deep fabric of the universe, changing the way nearby paths are arranged. And that makes spin one of the most important clues in black hole physics. Mass tells you how strong the gravitational presence is. Spin tells you how that presence moves. Together, they turn the black hole from a simple dark endpoint into a dynamic object with a hidden rhythm. It is darkness, yes, but not still darkness. It is a rotating depth, a place where the universe keeps the memory of motion even after the star that gave it that motion is gone. Kerr black holes, the realistic, rotating ones. The black holes most likely to exist in nature are not the perfectly still ones from the simplest textbook picture, but rotating Kerr black holes, shaped by motion that the universe almost never throws away. The idea begins with a useful contrast. The first clean model of a black hole imagined an object with mass but no spin, no charge, no extra complications. A calm mathematical doorway into understanding gravity. That model is powerful because it strips the problem down to its simplest form. But real cosmic objects are rarely born in perfect stillness. Stars rotate before they collapse. Gas clouds swirl before they fall inward. Galaxies turn. Binary systems twist around shared centers. When matter collapses into a black hole, the rotation it carried does not simply disappear. It becomes part of the black hole's final structure. This is where the Kerr black hole enters the story. Named after physicist Roy Kerr, who found the rotating solution to Einstein's equations in the 1960s, it describes a black hole with spin, and that single change makes the object feel much closer to the real universe. A Kerr black hole is not just a dark mass sitting quietly in space. It is a rotating gravitational system where the surrounding region is altered by angular motion. The event horizon is still there, the point beyond which return is impossible. But the space outside it is no longer as simple as in the non-rotating case. Rotation changes the allowed paths around the black hole, changes how close matter can orbit, and changes how energy behaves near the center. It also means the black hole can carry a trace of its past, not in the way a star carries layers or a planet carries mountains, but in the quiet fact of how fast it turns. A black hole that has fed from a steady disk for a long time may spin differently from one shaped by chaotic mergers or material arriving from many directions. This makes spin a clue, almost like a fossil of motion. Scientists do not study Kerr black holes only because the mathematics is elegant. They study them because nature probably makes them. The ideal motionless black hole is like a blank sketch. The Kerr black hole is the sketch given rotation, history, and realism. And this changes the emotional shape of the idea. A black hole is not only the end of a star or the center of gravity's deepest silence. It can also be a record of motion preserved after collapse, a place where the universe keeps turning, even after matter has lost its familiar form. In that sense, a Kerr black hole is not just a theoretical object. It is a reminder that reality is rarely perfectly still, and even darkness may have a spin. Frame dragging, when space-time is pulled around. A spinning black hole does not merely sit inside space-time, it can drag space-time around with it, as if the emptiness near it has learned to rotate. This effect is called frame dragging, and it is one of the strangest predictions of Einstein's gravity. To understand it, it helps to move away from the common picture of space-time as a stretched fabric, because near a rotating black hole, that image becomes too still. A better picture is a deep, invisible current. Far from the black hole, space behaves almost normally, and an object can define not rotating in a familiar way. But closer in, the black hole's spin begins to twist the local frame of reference itself. This means that the paths of objects, gyroscopes, gas, and even light are influenced not only by gravity pulling inward, but by space-time being carried around in the direction of the spin. Nothing is physically grabbing space like a hand grabs cloth. Instead, rotation becomes part of the geometry, and motion nearby is measured inside a world that is no longer perfectly still. Around Earth, frame dragging exists too, but it is extremely tiny, so small that it took careful satellite experiments to confirm it. Around a rotating black hole, the effect becomes far more intense. Matter orbiting in the same direction as the spin can behave differently from matter trying to move against it. The environment becomes asymmetric, not because the black hole has mountains or a surface, but because the space-time around it has a preferred swirl. This is why frame dragging feels so important. It shows that gravity is not only about mass-bending paths, but about motion, changing the very meaning of rest. Near a powerful rotating object, standing still is no longer a simple idea. The local stage itself is moving. A compass of motion, if such a thing existed, would not point to a universal stillness. It would be turned by the rotating geometry around the black hole. And this changes how you think about emptiness. Space is not a passive void where events happen. In extreme gravity, it can behave like an active participant, carrying information about mass, motion, and rotation. Frame dragging is the universe whispering that even nothing has structure. And near a spinning black hole, that structure can flow. It is not wind made of air, not water moving through a river, but a turning of the pathways that all things must follow. The black hole spins, and the nearby universe answers, not with sound, not with light, but with a slow, invisible rotation of reality's own frame. The ergosphere, a region where stillness is impossible. There is a region outside a spinning black hole where falling is not the strangest thing. The strangest thing is that standing still becomes impossible. This region is called the ergosphere, and it belongs only to rotating black holes, where space-time itself is dragged so strongly around the black hole that nothing inside this zone can remain motionless relative to the distant universe. That does not mean everything inside the ergosphere has already crossed the event horizon. This is the crucial difference. The ergosphere lies outside the point of no return, so escape is still possible from within it. But while you are there, you cannot simply hover in perfect stillness, as if space were a quiet room. The rotation of the black hole forces every possible object, particle, and beam of light to share in the turning motion. It is like entering a powerful current near a whirlpool. You may still have choices, you may still move, you may even escape, but you cannot pretend the current is not carrying you. The very definition of at rest has been taken away. Around a non-rotating black hole, the boundary of no return is the main dramatic line. Around a rotating one, nature adds this stranger outer zone where space-time has motion before escape becomes impossible. The ergosphere gets its name from energy because this is a place where rotational energy can, in principle, be taken from the black hole. That idea sounds almost unreal, but it comes from real physics. Under the right conditions, an object entering the ergosphere could split, with one part falling inward in a special way, while the other escapes carrying more energy than the original object had when it arrived. This is known as the Penrose process, and although it is not a simple machine we can build near a black hole, it shows something profound about rotating gravity. A spinning black hole is not only a trap, it is also a reservoir of motion. Its rotation can be part of what powers extreme cosmic environments. The ergosphere therefore feels like a threshold between danger and possibility. It is not safe, not calm, not ordinary, but it is not pure imprisonment either. It is a region where the universe says, you may leave, but you may not remain still. And that single idea is quietly terrifying, because stillness is one of the basic comforts of ordinary life. On Earth, you can stop walking, sit down, and feel the world hold steady around you. Near a rotating black hole in the ergosphere, that comfort becomes meaningless. Space is no longer a neutral background beneath your choices. It has become a turning environment, a dragged frame, a place where motion is woven into the rules themselves. The lesson is not just that black holes are powerful. It is that reality can contain regions where even rest is forbidden, where doing nothing is no longer an option, and where the deepest darkness in the universe does not merely pull things inward. It teaches space-time how to move, the Penrose process, and extracting energy. A rotating black hole is not only a place where energy disappears. Under the right conditions, it is also a place where energy can be taken from the rotation of space-time itself. This idea is called the Penrose process, and it begins in the strange region outside a spinning black hole where motion is forced to share the black hole's turn. The key is not to imagine someone drilling into a black hole or pulling power from inside the event horizon. Nothing useful comes back from there. The energy source is the black hole's spin, and the process happens outside the final boundary, in the zone where space-time is being dragged around so intensely that ordinary ideas of rest no longer apply. In a simplified version, imagine an object entering this rotating region and splitting into two pieces. One piece falls inward along a special path that, from the viewpoint of a distant observer, carries less than zero usable energy. That sounds impossible in everyday life, but near a spinning black hole, the way energy is counted can become unusual because the space-time itself is rotating. When that low energy piece drops into the black hole, it slightly reduces the black hole's spin. The other piece can escape outward with more energy than the original object had before it entered. The extra energy is not created from nothing. It is taken from the black hole's rotational energy, like a tiny withdrawal from a cosmic bank account built out of motion. This is why the Penrose process is so important. It shows that a black hole is not just a one-way sink, but a physical system with stored rotational energy that can, in principle, be extracted. In real astrophysics, nature may use related ideas through magnetic fields and plasma around spinning black holes, helping explain how some extreme jets and energetic outflows can be powered. It is not a simple machine, not science fiction fuel waiting for us to collect, but it is a real insight into how gravity, rotation, and energy interact near the edge of the possible. And there is something quietly profound in that. The black hole, which seems at first like pure loss, still obeys conservation. It can give up part of its spin. It can slow slightly as energy leaves its surroundings. Even darkness has an accounting. Even the most extreme object in the universe cannot escape the deeper balance of nature. The Penrose process teaches that energy is not only found in heat, light, or motion through space. Sometimes it is stored in the turning of space-time itself, waiting in a region where stillness has vanished and the universe has made rotation part of reality's hidden machinery. The singularity problem. At the deepest point of a black hole, science reaches a place where its most trusted language begins to tremble. This place is usually called the singularity, but the word can be misleading if you picture it as a tiny physical bead sitting at the center, like a dark grain hidden inside the universe. A singularity is better understood as a warning sign inside our theory, a place where the mathematics of general relativity points toward quantities becoming infinite, and our usual descriptions stop behaving in a sensible way. According to Einstein's gravity, when enough mass collapses beyond all known support, the inward fall does not simply stop at a solid surface. The theory says the collapse continues until density and curvature become extreme beyond limit. But here is the careful part. When a scientific theory gives infinity as an answer, it does not always mean nature truly contains an infinite object. Often, it means the theory has been pushed past the conditions where it can safely speak. It is like a map that guides you accurately across mountains, forests, and oceans. But then, at one forbidden edge, the lines twist together, and the paper says, "Beyond here, this map is no longer enough." That is the singularity problem. General relativity is extraordinarily successful at describing gravity on large scales, from planets to stars to the bending of light. But at the center of a black hole, it seems to collide with the need for a deeper theory. Gravity becomes incredibly strong. Matter is compressed beyond familiar forms, and the small-scale rules of quantum physics can no longer be ignored. The trouble is that we do not yet have a complete, tested theory that smoothly combines gravity with quantum behavior in this extreme region. So scientists do not honestly know what the center of a real black hole is like. It may not be an actual point of infinite density. It may be replaced by some unknown quantum structure, some new state of matter, or something our current concepts are not built to imagine. The important truth is not that there is definitely an infinite point inside every black hole, but that our present theories become strained when they try to describe what happens there. And that makes the singularity one of the most humbling ideas in physics. It is not just a monster at the center of darkness. It is a boundary of knowledge. It reminds you that science is powerful not because it pretends to know everything, but because it can recognize the places where its own tools begin to fail. A black hole hides its deepest interior from the outside universe. But the singularity problem hides something even more profound. The possibility that reality contains rules we have not yet learned how to read. And maybe that is why this idea feels so quiet and enormous. At the edge of the singularity, certainty does not grow louder, it becomes softer. It admits that the universe may be deeper than the theories we currently trust, and that the center of a black hole may not be an ending at all. But a question gravity has not yet taught us how to answer. Why singularities may not be the final answer. Singularity may be less like the final truth of a black hole, and more like a locked door with the wrong key still inside the lock. For a long time, the word singularity has carried a heavy, almost mythic feeling, as if physics has discovered an actual point where everything becomes infinitely crushed and all questions end. But many scientists are cautious with that picture, because infinity in a theory often means something more subtle. The theory is being asked to describe a realm it was not fully built to handle. General relativity is magnificent at explaining gravity as the shape of space-time, and it has passed many difficult tests, but it treats space-time as smooth, continuous, and classical. Quantum physics, on the other hand, tells us that at extremely small scales, nature may not behave like a smooth stage at all. It behaves in uncertain, granular, fluctuating ways, where energy, fields, and particles follow rules that feel deeply different from everyday intuition. The problem is that the inside of a black hole seems to demand both languages at once. Gravity is overwhelming, so general relativity cannot be ignored. The region is also pushed toward unimaginably tiny scales, so quantum physics cannot be ignored either. But we do not yet have a complete, experimentally confirmed theory of quantum gravity that unites them. That is why singularities may not be the final answer. They may be placeholders for something deeper, signs that our current map has reached a place where the next map must begin. Some approaches suggest that quantum effects could prevent matter from collapsing into a true infinite point, replacing the singularity with an extremely dense but finite state. Others explore whether the information and structure inside black holes might be described in a completely different way, perhaps through hidden quantum degrees of freedom, holographic ideas, or forms of space-time that are not smooth in the ordinary sense. These are not settled facts, and they should not be presented as certainty. They are attempts to answer a question that gravity has forced upon us. What happens when the largest scale force in the universe meets the smallest scale rules of nature? The honest answer is that we do not fully know, and yet that uncertainty is not a failure. It is one of the most productive tensions in modern physics. Black holes are not just objects we study from far away. They are pressure tests for reality itself. They ask whether space can break, whether time can end, whether information can survive, whether the universe permits true infinities or hides a deeper mechanism beneath them. A singularity, then, may not be a destination. It may be a symptom. It may be the universe quietly telling us that our best ideas are powerful, but incomplete. And perhaps the most beautiful part is that science does not need to pretend otherwise. It can stand at this dark threshold and say, "Here, we are not finished." Here, the old language bends. Here, somewhere beyond the reach of current equations and instruments, gravity and quantum reality may be waiting to become one story. So the center of a black hole may not be the place where knowledge ends forever. It may be the place where the next physics is still sleeping, hidden not because nature has no answer, but because we have not yet learned how to ask the question in the right way. Black holes and Einstein's general relativity. Einstein did not set out to invent black holes, yet his theory opened a door to them so extreme that even he was cautious about what it might mean. General relativity changed gravity from an invisible pull into something deeper, the shape and behavior of space-time itself. Before Einstein, gravity was often pictured as a force acting between objects, as if the sun reached across empty space and pulled Earth along its orbit. Einstein's idea was stranger and more elegant. Massive objects do not simply pull on the universe, they curve the stage on which motion happens. Planets, stars, and light follow paths through that curved stage. And what we call gravity is the result of those paths being shaped by mass and energy. A black hole is one of the most extreme tests of this idea, because it asks the theory to describe a place where space-time is not gently curved, not slightly distorted, but driven toward its most severe form. Around Earth, relativity is real but subtle. Around the Sun, it becomes measurable in the bending of starlight and the shifting orbit of Mercury. Around a black hole, it becomes impossible to ignore. The theory predicts that if enough mass is compressed into a small enough region, space-time can curve so deeply that a boundary forms from which no signal can return. This is not an added fantasy placed on top of Einstein's equations. It is a consequence that emerges when the theory is followed into its strongest gravitational territory. That is why black holes matter so much scientifically. They are not just strange objects in space. They are laboratories where general relativity is pushed toward its limits. Every star moving near a hidden center, every ring of light around a black hole's shadow, every gravitational wave from two black holes merging becomes a test of whether Einstein's description still holds when nature becomes extreme. And so far, again and again, general relativity has survived tests that would have destroyed a weaker idea. It has predicted the bending of light, the slowing of time in gravity, the existence of gravitational waves, and the behavior of compact objects with astonishing accuracy. But black holes also remind us that a powerful theory can be both successful and unfinished. General relativity describes the outside of black holes remarkably well, but when it is forced toward the deepest interior, it leads us to questions it may not be able to answer alone. That is what makes black holes feel like the theory's final exam. They prove the strength of Einstein's vision, while also exposing the places where future physics may be needed. They stand between triumph and mystery. A black hole says, "This theory can explain the shape of space-time better than anything before it." But it also asks what happens when space-time is pushed beyond every familiar condition. And perhaps that is the most beautiful part. Einstein gave humanity a new way to understand gravity, not as a simple tug, but as the architecture of reality. Black holes are where that architecture becomes cathedral-like and terrifying, vast in implication, dark in appearance, and precise enough to test with telescopes and detectors. They are not just predictions of general relativity, they are its most dramatic witnesses, quietly showing that the universe is not built on the common sense of everyday life, but on a deeper geometry where space bends, time stretches, light curves, and darkness itself can become evidence of a theory still echoing more than a century after it was born. Schwarzschild, black holes. The simplest black hole in physics is not the most realistic one, but it is the cleanest doorway into understanding what a black hole means. This model is called a Schwarzschild black hole, named after Carl Schwarzschild, who found an exact solution to Einstein's gravity shortly after general relativity was introduced. What makes it simple is what it removes. A Schwarzschild black hole does not spin. It has no electric charge. It is perfectly spherical, perfectly still, and described only by its mass. In the real universe, many black holes probably rotate, and their surroundings can be messy with gas, magnetic fields, companion stars, and violent motion. But the Schwarzschild model strips all of that away, leaving a quiet, pure version of the idea. What happens when gravity belongs to a compact mass with no extra complications? In this model, the black hole is not imagined as a material ball with a hard surface. Instead, the important feature is the Schwarzschild radius, the distance from the center where the event horizon forms. If the mass is packed inside that radius, the region becomes a black hole. The larger the mass, the larger this horizon. That is a beautifully simple rule, because it lets scientists talk about black holes without first needing to know every detail of their birth, their environment, or their motion. A Schwarzschild black hole is like the clean outline of a mountain before weather, forests, roads, and shadows are added. It shows the essential shape of the problem. Far away, gravity behaves in a familiar way, weakening with distance. Closer in, the curvature becomes stronger. At the horizon, the ability to send signals outward ends. Inside, according to the classical model, all future paths move inward. The value of this model is not that nature must produce perfect Schwarzschild black holes everywhere, but that it gives physics a calm foundation. It lets scientists define basic ideas clearly. Horizon, radius, shadow, gravitational time dilation, and the strange difference between what distant observers infer and what falling objects experience. It also teaches a philosophical lesson about simplicity. Sometimes the universe is too complex to understand all at once, so science begins by removing everything that is not essential. The Schwarzschild black hole is that first quiet sketch, not the whole painting, not the final portrait of every real black hole, but the essential silhouette. And in that silhouette, you can see why black holes became such powerful objects in science. With only mass and gravity, without surface, flame, spin, or charge, the universe can still create a boundary so absolute that it changes the meaning of escape. Charged black holes in theory. A charged black hole sounds like the universe has added electricity to darkness, but in real astronomy, this is probably one of the rarest kinds of black holes nature could keep for long. In theory, a black hole can have electric charge, just as an object can have more positive or negative charge than its surroundings, and physicists study these models because they reveal how gravity and electromagnetism might interact under extreme conditions. The most famous simple charged model is called a Reissner-Nordström black hole, and it begins with a clean idea. Take a black hole, give it mass, give it electric charge, but do not let it spin. This creates a different kind of theoretical object from the simple non-rotating, uncharged model. The charge changes the structure around the black hole, because electric forces are much stronger than gravity on the scale of individual particles. If a black hole had a strong positive charge, it would attract negative particles from nearby space and repel positive ones. If it had a strong negative charge, it would do the opposite. That is why large, long-lasting charged black holes are not expected to be common in the real universe. Space is not perfectly empty. It contains plasma, particles, gas, radiation, and magnetic environments. A black hole with a strong charge would quickly attract opposite charges toward itself, reducing the imbalance, almost like nature trying to neutralize the object. This does not make charged black holes useless as an idea. It makes them valuable as a theoretical laboratory. They allow scientists to ask, what happens when an event horizon is shaped not only by mass, but by electric fields? How does the presence of charge change the possible boundaries around a black hole? In some idealized charged models, the geometry can contain more than one horizon, including an inner horizon deep inside the outer one, though what actually happens in such regions may be unstable and difficult to describe physically. This is why charged black holes have a different flavor from the black holes most astronomers expect to observe. They feel less like common cosmic remnants and more like precise thought experiments. Strange clean rooms where physics can test how its laws behave when pushed into extreme combinations. They also remind you that black hole is not one single personality. Change mass, spin, or charge, and the object's theoretical structure changes. But charge is special because nature seems eager to erase it on large scales. Stars and planets may contain countless charged particles, yet they are usually nearly neutral overall, because positive and negative charges balance with astonishing precision. A black hole formed from real matter would likely inherit that near-neutral state, and any strong imbalance would be corrected by its environment. So a charged black hole is not something to picture as a common electric monster drifting through space. It is better understood as a rare possibility, a mathematical edge case, a controlled thought in the deeper story of gravity, and perhaps that is its quiet lesson. Not every idea in physics has to be common in the sky to be important. Some ideas matter because they show what nature allows in principle, where the boundaries of theory are, and how even darkness can be given different identities when the universe changes just one hidden property. No-hair theorem. Black holes forget their past. A black hole may be the only object in the universe that can erase almost everything about how it was made. This idea is known as the no-hair theorem, and despite its strange name, it points to one of the cleanest and most unsettling truths in black hole physics. Once a black hole settles down, the outside universe may be able to describe it using only a tiny amount of information. In ordinary life, objects carry history in their details. A planet remembers its past through craters, mountains, oceans, atmosphere, and chemistry. A star remembers its life through its composition, brightness, temperature, and layers. Even a burned piece of wood still carries clues about what it once was. But a black hole is different. If a black hole forms from a collapsing star, or from two black holes merging, or from matter falling inward over long periods of time, the messy story of that formation does not remain visible in the way you might expect. The original star's shape, its storms, its chemical layers, its magnetic scars, its surface patterns, its private complexity, all of that is hidden from the outside once the black hole becomes calm. What remains in the classical picture is mainly a small set of properties: how much mass it has, how fast it spins, and whether it carries electric charge. The phrase "no hair" is a metaphor. Hair would mean extra details, little distinguishing features, personal marks that make one black hole visibly different from another. The theorem says that black holes do not keep those details in a way the outside universe can easily read. Two black holes with the same basic properties would be indistinguishable from the outside, even if one was born from a giant star and the other grew through a long chain of mergers. This does not mean the past never happened. It means the past is no longer available in the black hole's outward identity. During formation, violent events can send out light, particles, or gravitational waves, and those signals may carry some record of what occurred. But after the black hole settles, it becomes strangely simple, like a sealed book whose cover shows only a few numbers while the pages inside can no longer be opened. This is why the no-hair theorem feels both elegant and disturbing. Nature usually loves complexity. Clouds have shapes, galaxies have arms, stars have spectra, planets have surfaces. But black holes seem to compress identity itself. They take rich histories and reduce them to a minimal gravitational signature. A black hole does not display biography, it displays outcome. And in that reduction, there is a deeper question waiting quietly. If the outside universe cannot read the details anymore, where did those details go? Are they truly lost, hidden in a way we do not yet understand, or transformed into some deeper kind of information? That question leads towards some of the hardest problems in modern physics, but the no-hair theorem is where the emotional shock begins. It tells you that a black hole is not only a place where matter can disappear from view, it is a place where difference itself seems to fade. The universe can pour in stars, gas, light, and history, yet the final object may answer with almost nothing personal, and perhaps that is what makes black holes so haunting. They are not chaotic in the way you expect. They are terrifyingly simple. They forget the noise, the shape, the origin, the drama. They keep only the few clues gravity allows them to show, standing in the dark like monuments to everything that once had a story, and then became almost perfectly silent. Mass, spin, and charge, the three clues. A black hole's identity card is shockingly small, not a long biography, not a list of everything it swallowed, but only three clues the outside universe may be allowed to read. Those clues are mass, spin, and charge. Mass is the most important one because it tells you how much gravitational presence the black hole carries. A more massive black hole has a larger event horizon, stronger influence over nearby motion, and a deeper effect on the surrounding space-time. If you know its mass, you know a great deal about the scale of the object, even if you know nothing about the star that died to make it, or the gas that later fell toward it. Spin is the second clue, and it tells a different kind of story. It is not about how much matter the black hole contains, but how much rotation it keeps. A spinning black hole changes the environment around it, pulling nearby space-time into a rotating structure and altering the paths available to matter and light. Spin can hint at history, because black holes may spin up when they gather material in a steady direction, or change their rotation through collisions and mergers. It is like a faint record of motion preserved after almost every visible feature has disappeared. Charge is the third clue, but in the real universe it is probably the quietest one. A black hole can have electric charge in theory, yet strong charge is unlikely to last long in space because opposite particles would be attracted and tend to neutralize it. So when astronomers think about real black holes, mass and spin usually matter far more, while charge is often expected to be very small. Still, charge belongs on the identity card because the laws of physics allow it, and because it completes the classical description of what a settled black hole can show from the outside. The strange part is what is missing. There is no line for the color of the original star, no record of its storms, no list of the elements that once burned inside it, no memory of whether the black hole formed through one collapse or grew through many events. The rich past is compressed into a minimal present. This is not because the past was meaningless, but because the outside world cannot easily access it once the black hole has settled. A black hole becomes a kind of cosmic citizen, with only a few visible documents: how heavy it is, how it turns, and whether it carries charge. Everything else becomes hidden behind the simplicity of its gravitational face. And that simplicity is what makes black holes so unsettling. Most objects become more interesting the closer you look. They reveal textures, layers, histories, scars. A black hole becomes stranger because it does the opposite. It reduces identity to essentials. It takes complexity and answers with silence. Yet from those three clues, scientists can still build a powerful picture. How large the horizon should be, how nearby matter may orbit, how energetic the surrounding region can become, and how the black hole may have grown. In the end, mass, spin, and charge are not just labels. They are the last readable fragments of a much larger story, the only pieces of a hidden biography that gravity still permits the universe to see. Black hole entropy. A black hole becomes even stranger when you stop asking what it swallows and start asking what it remembers. This is where black hole entropy enters, quietly, almost like a hidden accounting system written on the edge of darkness. In ordinary life, entropy is often described as disorder, but a deeper way to think about it is as a measure of how many hidden arrangements could produce the same visible state. A warm cup of coffee, a cloud of gas, a room full of moving air. Each can look simple from the outside while containing an enormous number of microscopic details inside. Entropy tells us that those unseen details matter. They are part of the physical bookkeeping of the universe. Now place that idea near a black hole. If matter falls in, it carries information with it. energy, particles, arrangements, structure, history. From the outside, much of that detail becomes unavailable. The black hole does not show you the shape of the object that fell in, the pattern of atoms, the exact story of what crossed the boundary. It seems to hide complexity behind a simple gravitational face. But physics has a deep rule. Information and entropy cannot simply be ignored as if they never existed. If you throw a highly entropic object into a black hole, the outside universe loses access to that object's details. So where does the entropy go? The shocking answer is that the black hole itself must have entropy. It is not just a dark object with mass. It behaves, in a thermodynamic sense, like something with hidden states, something that can be counted, compared, and understood through the language of information. And the strangest part is where that entropy seems to live. For ordinary objects, you might expect the amount of hidden information to grow with volume, with how much space is inside. But black holes point towards something more mysterious. Their entropy is connected to the area of the event horizon, the boundary around the black hole, rather than the volume within. That idea feels almost impossible at first, as if the universe was saying that the secret of what lies inside is written on the surface that hides it. The horizon becomes more than a point of no return. It becomes a kind of informational skin, a place where gravity, thermodynamics, and quantum theory begin to touch. This does not mean the horizon is a literal hard drive with visible letters carved into it. It means that when scientists calculate the entropy of a black hole, the surface area of that boundary plays the central role. And this changed physics deeply, because it suggested that space, information, and gravity may be more connected than anyone expected. A black hole, then, is not only a place where light cannot return, it is a clue that the universe keeps track of hidden information in ways our everyday intuition was never built to understand. Its darkness is not empty silence. It may be the most compressed form of bookkeeping nature allows. The Bekenstein-Hawking area law. A black hole seems as if its secrets should be hidden deep inside. Yet one of the strangest discoveries in physics says the amount of hidden information is tied to its surface. This idea is known as the Bekenstein-Hawking area law, and it quietly overturns one of the most natural assumptions your mind makes about reality. In ordinary life, when you want to store more things, you think about volume. A bigger room holds more furniture, a larger box holds more objects, a deeper library holds more books. Space inside seems like the place where information should live. But black holes tell a different story. When Jacob Bekenstein began thinking about black hole entropy, and Stephen Hawking later connected black holes with radiation and temperature, a surprising pattern emerged. The amount of entropy associated with a black hole does not grow with the volume hidden behind the horizon, but with the area of the horizon itself. In simple words, the boundary matters more than the interior. The surface surrounding the black hole seems to count how much hidden information the black hole can have. This does not mean the horizon is a physical wall covered with tiny writing, or that information is stored there in a simple mechanical way like files on a screen. It means that when physics tries to measure the black hole's hidden complexity, the calculation points to the size of the outer boundary, not the amount of space inside. That is deeply strange, because it suggests that gravity may treat information differently from ordinary matter. A black hole can grow larger by absorbing energy and mass, and as its horizon expands, its possible hidden states expand too. The size of its informational capacity is written by the area of the edge that separates what can still communicate with the outside from what cannot. This is why the area law became one of the seeds of much bigger ideas, including the possibility that information in a region of space might be describable by data on a boundary. That thought would later inspire the holographic principle, but the area law is where the door first begins to open. It makes the universe feel less like a set of containers and more like a system of surfaces, limits, and relationships. The deepest lesson is not that we fully understand what happens inside a black hole. We do not. The lesson is that black holes force us to rethink where reality keeps its records. Maybe information is not always stored where intuition expects. Maybe the edge of a region can say more than the depth behind it. And maybe the event horizon, which first appeared as a boundary of silence, is also a boundary of accounting, a place where gravity and information meet in a way that still feels unfinished. The Bekenstein-Hawking area law does not make black holes less mysterious. It makes their mystery sharper. It tells you that the universe may keep count not by filling darkness with volume, but by measuring the surface of the darkness itself. Hawking radiation. A black hole seems like the perfect prison for light. Yet Stephen Hawking showed that even this prison may have the faintest possible leak. Hawking radiation is one of the most delicate and surprising ideas in modern physics, because it does not come from ordinary matter shining near the black hole, and it does not mean that something escapes from inside the event horizon after crossing it. Instead, it comes from the strange meeting point between quantum physics and curved space-time. In quantum theory, empty space is not perfectly empty in the simple, silent way our senses imagine. Fields are still present, and at tiny scales there is a kind of restless uncertainty built into nature. Near the horizon of a black hole, this quantum restlessness is affected by the extreme gravitational environment. The result, according to Hawking's calculation, is that a black hole should behave as if it has a temperature and can slowly emit radiation. The common picture says that pairs of particles appear near the horizon, one falling in while the other escapes. But this is only a rough metaphor. The deeper truth is more subtle. What different observers call empty space is not always the same near such extreme gravity, and that difference can appear as real radiation far away. The important lesson is calm but enormous. A black hole is not completely eternal in the classical sense. If it emits radiation, it loses a tiny amount of energy. And because energy and mass are linked, the black hole very slowly loses mass as well. For large astrophysical black holes, this effect is unbelievably weak. A black hole with the mass of a star would radiate so faintly that the universe around it easily overwhelms the signal. It is not glowing like a candle. It is not visibly steaming away. It is losing energy at a pace so slow that, for practical cosmic history, it behaves almost like permanence. But almost is the word that changes everything. Hawking radiation tells us that black holes are not just objects of gravity, they are also objects of thermodynamics and quantum theory. They have temperature, they have entropy, they participate in the universe's deeper accounting. This turns the black hole from a simple endpoint into a bridge between the greatest theories we have and the theory we still lack. It suggests that even the darkest boundary in nature is not outside the laws of change. Slowly, quietly, across timescales far beyond human imagination, a black hole may give something back to the universe. Not light from its interior, not a message from what fell in, but a faint quantum whisper from the edge where gravity and uncertainty meet. And that is why Hawking radiation feels so profound. It softens the idea of absolute darkness. It says that even a black hole is not pure silence forever. Somewhere in the mathematics of the horizon, the universe has written a slow, almost invisible reminder that nothing physical is completely beyond transformation. Do black holes eventually evaporate? The end of a black hole is not an explosion at midnight, but a fading so slow that the universe must grow old beyond imagination before the question even becomes real. If Hawking radiation is correct, then black holes do not remain absolutely unchanged forever. They can lose energy, and because energy and mass are connected, they can very gradually lose mass. But the word gradually almost fails here. A black hole born from a star would take far longer than the current age of the universe to evaporate. Not just a little longer, but so much longer that ordinary time comparisons stop feeling useful. Supermassive black holes would last even more absurdly long, surviving into eras when stars may have burned out, galaxies may have grown dim, and the bright, busy universe we know may have become a cold, thin memory. In the present age, large black holes are not really shrinking in any meaningful way because they can still absorb surrounding radiation and matter, including the faint glow left from the early universe. Only in a far future, when the universe has expanded and cooled enough, would many black holes begin to lose more than they gain. Then, over unimaginable stretches of time, evaporation would become their slow destiny. The strange part is that evaporation does not proceed like melting ice in warm air. A black hole gets slightly hotter as it loses mass, so the smaller it becomes, the faster the process grows. For most of its life, the change is almost silent. Near the very end, if our theories remain valid there, the process could become much more energetic. But we must be careful. The final stage of evaporation is exactly where our current physics becomes uncertain, because the black hole would be extremely small and quantum gravity may matter strongly. We do not yet know the last frame of the story with confidence. It may end in a final burst, or something more subtle may occur that our present theories cannot fully describe. What we can say is enough to make the mind quiet. Black holes may be the longest-lived objects in the cosmos, but even they may not be permanent. They are not eternal monuments carved outside time. They are physical systems with a temperature, a history, and possibly an ending. This changes the emotional shape of the black hole. At first it seems like the ultimate winner over change, a thing that outlasts stars, planets, and light. But Hawking's idea gives it a future as fragile as it is vast. The black hole may wait through ages so long that no star remains to watch it, slowly returning its mass to the universe as faint radiation. And perhaps that is the deepest lesson hidden in cosmic time. Permanence may only be a matter of scale. Some things vanish in seconds, some in billions of years, and some may take so long that disappearance itself becomes almost indistinguishable from eternity. Yet even then, the universe keeps moving, and even the darkest objects may one day become part of the quiet background they once seemed to escape. Why Hawking radiation is almost impossible to detect. The most famous glow a black hole may produce is also the one we are least likely to see. Hawking radiation sounds dramatic when you first hear about it, as if every black hole should be surrounded by a faint visible mist, slowly shining itself away into space. But the real picture is far colder, quieter, and more difficult. For ordinary astrophysical black holes, the kind formed from massive stars, or the supermassive giants at the centers of galaxies, Hawking radiation is not only weak, it is almost buried beneath the universe itself. The reason is that the temperature of Hawking radiation becomes lower when the black hole is more massive. A black hole with the mass of the Sun would have an extremely tiny temperature, far colder than the cosmic microwave background, the leftover glow that fills space from the early universe. That means the black hole is not standing out as a warm object against a cold background. It is colder than the background around it. Instead of noticeably radiating away, it can still absorb more energy from its environment than it loses through Hawking radiation. For supermassive black holes, the situation becomes even more extreme. Their Hawking temperature is so incredibly small that detecting their radiation directly is far beyond anything our instruments can do. And the problem is not only faintness. Real black holes are rarely isolated in perfectly empty darkness. They may sit near gas, dust, stars, magnetic fields, high-energy particles, and radiation from many other sources. Matter near black holes can produce X-rays, radio waves, and intense light from hot accretion disks or jets. And all of that ordinary astrophysical activity is vastly louder than Hawking radiation. Trying to detect Hawking radiation from such a black hole would be like trying to hear a single grain of sand touch the floor during a thunderstorm. The signal is not just small, it is hidden under stronger, messier, more familiar signals. Smaller black holes would radiate more strongly, and very tiny black holes, if they existed, could be much hotter and easier to notice. But here, the story becomes careful again. Such tiny black holes are hypothetical in astronomy. They might have formed in the early universe under special conditions, but no confirmed primordial black hole has been observed. Scientists search for possible signs, such as unusual bursts of high-energy radiation, but there is no settled detection that proves Hawking evaporation from a real cosmic black hole. This is why Hawking radiation sits in a strange place in science. It is deeply respected as a theoretical result, one that links gravity, quantum fields, temperature, and entropy in a powerful way. Yet it remains extraordinarily hard to verify directly in the sky. Some laboratory systems can imitate certain horizon-like effects and produce analog radiation, helping researchers explore related physics. But those are not actual black holes in space. They are controlled echoes, not the cosmic event itself. So the honest lesson is not that Hawking radiation is easy to find, but that nature sometimes hides its most important truths behind signals too faint for the present age to hear. Black holes may be slowly whispering through quantum radiation, but the universe is loud, warm, bright, and full of interference. For now, Hawking radiation is less like a beam seen through a telescope and more like a prediction waiting at the edge of possibility, reminding us that the deepest laws may be real long before they become observable. And that gives the idea a quieter kind of beauty. The black hole may be speaking, but in a voice so soft that science must first learn how to silence the whole universe around it. The information paradox. If the universe keeps a record of everything that happens, then a black hole asks the most dangerous question in physics. Can that record be destroyed? This is the information paradox, and it is not about information in the everyday sense of names, memories, or written messages. In physics, information means the complete physical description of a system, the arrangement of particles, their properties, their relationships, the hidden details that make one state of reality different from another. Quantum physics strongly suggests that this kind of information is never truly lost. It may become scrambled, spread out, impossible for us to practically recover. But in principle, the universe should not simply erase the difference between what happened and what did not happen. A burned book is a useful example. To you, the words are gone. The pages are ash, smoke, heat, and scattered molecules. But according to the deeper laws, the physical traces of that burning still carry the story in an unimaginably scrambled form. The information has not vanished, it has become inaccessible. Black holes make this comforting idea tremble. Matter falls in carrying detailed information, but the outside world can no longer inspect those details directly. Then Hawking radiation enters the story, because if a black hole slowly emits radiation and eventually shrinks away, what happens to everything that fell inside? Hawking's original calculation suggested that the radiation looks almost thermal, meaning it appears to carry little or no detailed imprint of the objects that formed or entered the black hole. If the black hole completely evaporates and the radiation carries no record, then the information seems to have disappeared from the universe. That would clash with one of the deepest expectations of quantum theory. But if information is not destroyed, then it must somehow escape, be preserved, or be encoded in a way our simplest picture does not reveal. This is why the paradox is so powerful. It is not merely a puzzle about black holes, it is a collision between two great languages of nature. General relativity tells us that the horizon can hide events from the outside. Quantum physics tells us that the full story of a physical system should not be deleted. Both theories are extraordinarily successful, yet when they meet at the edge of a black hole, they seem to pull truth in different directions. Modern research has offered many possible paths. Perhaps information is subtly encoded in Hawking radiation. Perhaps the horizon stores or scrambles information in a deeper way. Perhaps space-time itself must be understood differently when quantum gravity is included. But the honest answer is that the final explanation is still one of the great open questions, and that uncertainty is what gives the information paradox its philosophical weight. It asks whether reality is allowed to forget. It asks whether the past is only hidden, or whether the universe can truly erase it. It turns a black hole from a dark astronomical object into a courtroom for the laws of nature, where gravity, quantum theory, time, and memory all stand as witnesses. Maybe information survives in a form too subtle for ordinary intuition. Maybe the final theory will show that nothing is ever lost, only transformed beyond recognition. But until that theory is complete, the black hole remains a quiet challenge at the edge of knowledge, asking whether the universe is a perfect keeper of its own history, or whether even reality has places where the story can disappear. Black hole complementarity. Two observers can watch the same black hole event and come away with stories that seem to contradict each other, yet physics may allow both stories to be true in their own place. This is the strange idea behind black hole complementarity, a proposal created to soften one of the sharpest tensions in black hole physics. The tension begins when you ask what happens to information that falls toward a black hole. From the point of view of a distant observer, the object never simply gives back a clear message after crossing the horizon. Its signals become harder to receive, more redshifted, more delayed, and eventually lost in practice. But quantum theory strongly resists the idea that physical information can be destroyed. So one possible answer is that, to the outside universe, the information is somehow absorbed, scrambled, and later returned in an extremely subtle form through the black hole's radiation. From that outside perspective, the horizon behaves almost like a place where information is processed and re-expressed, not simply erased. But now imagine the falling observer. According to ordinary general relativity, especially at the horizon of a large black hole, that person may not encounter a dramatic surface at the exact crossing point. There is no obvious wall in the classical picture, no instant signal saying, "You have reached the boundary." The falling observer simply continues inward, carrying their own experience with them. So whose story is correct? Did the information stay encoded at the horizon for the outside world? Or did it fall through with the traveler? Black hole complementarity says that these two descriptions may not need to be combined into one single viewpoint. They may be complementary descriptions, each valid for the observer who can actually make the measurements. The distant observer cannot enter the black hole, collect the interior copy, and compare it with the outside radiation. The falling observer cannot return to the outside universe and check what was later emitted. No single observer can witness both versions in a way that creates a direct contradiction. This is not a trick to avoid the problem. It is an attempt to respect a deep lesson from modern physics. What reality looks like can depend on what can be observed, communicated, and compared. Complementarity does not say anything goes. It does not mean black holes are magic or that truth is purely personal. It means the laws may protect consistency by preventing one observer from accessing both accounts at once. In that sense, the black hole becomes a boundary not only in space but in knowledge. It separates descriptions that cannot be stitched together by ordinary experience. This idea is powerful because it makes the event horizon feel less like a simple line and more like a philosophical filter. Outside, information may appear to be preserved in one form. Inside, the falling observer may experience a different continuation. Both stories are incomplete alone, but neither observer can prove the other wrong from within their own accessible world. And that leaves you with a quiet, unsettling question. Perhaps reality is not always a single story told from nowhere. Perhaps in the most extreme places, the universe allows different observers to hold different pieces of truth, not because truth has broken, but because no one is allowed to stand everywhere at once. The firewall hypothesis. The firewall hypothesis begins with a disturbing possibility. What if the event horizon is not always the quiet crossing that classical gravity once promised, but a violent place where the old picture of a black hole breaks apart? This idea is speculative, and it should be treated carefully. It is not an observed feature of real black holes, and scientists do not agree that firewalls truly exist. But the reason the idea matters is that it exposes a deep tension in the way we try to combine black holes with quantum theory. In the traditional picture from general relativity, especially for a very large black hole, crossing the event horizon might not feel special at the exact moment you pass it. There is no solid surface there, no obvious wall, no sudden flash built into the classical theory. But quantum physics adds a different demand. If black holes slowly radiate and eventually disappear, the information connected to what fell in should not be destroyed. To preserve that information, the outgoing radiation may need to carry subtle correlations with earlier radiation that already escaped. Here is where the trouble begins. The same outgoing radiation in the smooth horizon picture also seems tied to something inside the black hole in a way that helps empty space near the horizon look normal to a falling observer. But quantum rules limit how strongly one thing can be fully linked with two different partners at once. In simple language, the radiation cannot perfectly serve two masters. It cannot both preserve the outside information story and also maintain the smooth interior story in the naive way. The firewall hypothesis offers a brutal solution. Maybe the smooth horizon is sacrificed. Maybe, instead of passing through peacefully, an infalling observer would encounter a high-energy barrier at or near the horizon, something like a wall of destructive radiation. That is why it is called a firewall. But this is not a literal wall of ordinary flame, and it is not a science fiction force field. It is a proposed quantum effect, a possible sign that the horizon is more violent than general relativity suggests when information preservation is taken seriously. The emotional power of the idea comes from what it threatens. It challenges the equivalence principle, one of Einstein's deepest insights. The idea that a freely falling observer should locally feel normal physics, even in a gravitational field. If firewalls are real, then the horizon is not just a boundary of communication. It becomes a place where the rules themselves announce their conflict. Yet many physicists are uncomfortable with this conclusion because it seems too extreme, too costly, and perhaps a sign that we are missing a subtler theory. Other approaches try to preserve both information and a smooth horizon through deeper quantum gravity, holography, or new ways of understanding space-time. So the firewall hypothesis should not be presented as the final answer. It is more like an alarm bell inside modern physics. It says, if we insist on certain principles all at once, something may have to give. And that is what makes it fascinating. A black hole, already strange as an object of gravity, becomes a test of what reality values more deeply. Smooth space, preserved information, or some hidden principle we have not yet named. The firewall may never be found in nature, but the question it raises remains sharp. When the universe is forced to choose between its best laws, does one law break? Or do we discover that the laws were never separate in the first place? The holographic principle. The holographic principle begins with a thought so strange that it sounds like a dream. Yet it was born from serious attempts to understand black holes. Maybe the information inside a region of space can be described by what happens on its boundary. Not because the universe is a literal projection on a wall, and not because reality is fake in the simple way science fiction sometimes suggests, but because black holes taught physics something deeply unexpected. When scientists studied black hole entropy, they found that the amount of hidden information associated with a black hole grows with the area of its horizon, not with the volume hidden behind it. That discovery raised a quiet but enormous question. If the most extreme object in nature stores information according to surface area, could this reveal something general about gravity itself? The holographic principle is an answer in that direction. It suggests that, in certain deep descriptions of physics, the full story of a space may be encoded on a lower dimensional boundary surrounding it. The name comes from a hologram, where a flat surface can contain information that appears three-dimensional. But this is only an analogy. The real idea is more subtle and mathematical. The information needed to describe a gravitational region might not scale the way ordinary intuition expects. This does not mean your room is secretly painted on the walls, or that your life is an illusion playing from the edge of the cosmos. It means that at the deepest level, space, gravity, and information may be more tightly connected than our everyday experience suggests. One of the strongest inspirations for this idea comes from theoretical work. showing that some universes with gravity can be equivalent to different descriptions without gravity on their boundaries. In those cases, two very different looking theories may describe the same physics, like two languages telling one story. That is why the holographic principle matters. It hints that space-time may not be the most basic ingredient of reality. Space might emerge from patterns of information, from relationships, from deeper quantum structure, rather than existing as an empty container that simply waits for things to happen inside it. Black holes make this possibility hard to ignore because they behave as if boundaries have a surprising power. The edge is not merely an edge. It may be where the bookkeeping of reality becomes visible. And this idea changes the emotional feeling of the universe. You may think depth is where secrets live, that the truth of a place must be hidden far inside it. But black holes whisper the opposite possibility. Sometimes the boundary carries the story. Sometimes the surface knows more than the volume. The holographic principle remains an open and profound idea, not a finished explanation of everything, but it gives physics a new way to ask what space really is. Black holes as nature's hard drives. The strangest hard drive in nature would not look like a machine at all. It would look like a black hole, silent, dark, and almost completely unreadable from the outside. Calling black holes nature's hard drives is only a metaphor, but it points toward a real and serious idea in physics. Black holes may be the most extreme information storage systems the universe allows. In an ordinary computer, information is arranged in patterns you can read, copy, erase, and organize. A file has structure. A memory chip has circuits. A hard drive has physical states that represent data. A black hole is nothing like that in a practical sense. You cannot plug into it. You cannot open a folder inside it. You cannot send a message through the horizon and expect it to come back. But when physicists talk about information, they mean something deeper than human data. They mean the physical details that distinguish one possible state of the universe from another. Every object that falls toward a black hole carries such details. Not only its mass, but the arrangement of its particles, its quantum state, its motion, its history of interactions. The mystery is that, from the outside, the black hole appears to hide almost all of this detail behind an extremely simple identity. Yet black hole thermodynamics suggests that this hidden complexity does not simply vanish from the bookkeeping of nature. Instead, the black hole has an enormous capacity for information, and that capacity is tied to the size of its horizon. In that sense, the horizon behaves less like a normal surface and more like a limit on how much hidden physical information can be associated with the object. The more mass and energy a black hole gains, the larger its horizon becomes, and the greater its possible hidden states become. This is why the hard drive metaphor is tempting. A black hole can absorb information in the most absolute-looking way imaginable, but the metaphor must be handled carefully. A normal hard drive stores information so that it can be retrieved by a user. A black hole, if it preserves information, seems to scramble it beyond ordinary recognition. It may mix the details so thoroughly that recovering them would be like reconstructing a library from warm smoke, except even harder, because gravity and quantum effects are involved at the deepest level. Some modern ideas suggest that information might not be destroyed, but encoded subtly in the black hole's boundary, or in the radiation it eventually emits. That would make a black hole less like an eraser and more like a cosmic scrambler, a system that takes clear structure and transforms it into a form no ordinary observer can decode. And this is where the idea becomes quietly unsettling. Human memory depends on access. A memory you can never recall feels almost like a loss. But physics asks a sharper question. Is information lost because no one can read it, or only if the universe itself no longer contains it? Black holes force that distinction into the open. They may store, hide, scramble, and slowly release information in ways that challenge the meaning of storage itself. So when you picture a black hole as nature's hard drive, do not imagine a device waiting in space with neat files inside. Imagine instead the ultimate limit of compression, a place where matter, energy, and history are reduced to hidden physical possibilities, where the universe may keep records in a language too deep for direct reading. And perhaps that is the most haunting lesson. The darkest object in the sky may not be empty of information. It may be full of it, not arranged for understanding, not available to touch, but sealed into the structure of gravity itself. As if nature keeps its most difficult memories behind a door no ordinary light can open. Gravitational waves from black hole mergers. When two black holes merge, the universe does not scream through light. It trembles through the shape of space itself. These trembles are called gravitational waves, and they are one of the most beautiful predictions of Einstein's gravity. Not waves moving through space-time, like sound through air, but waves of space-time, tiny stretches and squeezes traveling outward at the speed of light. To understand them calmly, picture two black holes orbiting each other in the dark, not touching, not shining by themselves, but carrying enormous mass through a tightening dance. As they circle, they disturb the geometry around them. The distortion does not stay still. It travels away, spreading through the cosmos like ripples across a pond, except the pond is reality's own structure. These waves carry energy, and because energy leaves the system, the two black holes gradually spiral closer together. The orbit shrinks, the motion speeds up, the waves become stronger and more frequent. In the final moments before merger, the dance becomes almost unimaginably intense. A huge amount of energy can be released in gravitational waves in less than a second, not as fire, not as ordinary radiation, but as a passing vibration in space-time. Then the two horizons combine into one larger black hole, and the newly formed object rings down, settling into a calmer shape, like a struck bell, slowly losing its vibration. The remarkable thing is how subtle these waves are when they reach Earth. By the time they cross our planet after traveling for millions or even billions of years, they change distances by less than the width of a proton over kilometer-scale detectors. That sounds impossible to measure, yet instruments like LIGO and Virgo were built to do exactly that, using laser beams and long arms to sense the tiniest stretching and squeezing of space. When a gravitational wave passes, one direction becomes minutely longer, while another becomes minutely shorter. Then the pattern reverses. Nothing explodes in the detector. No telescope sees a flash. The signal is a brief change in distance, a faint pulse from an event that happened far away and long ago. This is why gravitational waves opened a new sense for astronomy. Before them, humanity mostly studied the universe through light, visible light, radio waves, X-rays, infrared, and other forms of electromagnetic radiation. But black hole mergers may produce little or no light at all. Gravitational waves let us detect events that would otherwise remain hidden, allowing us to hear the dark side of the cosmos through motion rather than brightness. They tell us the masses of the black holes, how fast they spiral together, and whether the final object behaved the way general relativity predicts. Each detection is not just an observation, it is a message carried by space-time itself. And there is something deeply humbling about that. Somewhere in the darkness, two invisible objects can collide, and for a brief moment, they can shake the universe so gently that after crossing unimaginable distances, the wave barely touches our instruments, and yet we can still know it happened. Gravitational waves teach that the universe does not need light to speak. Sometimes it speaks by stretching distance, by compressing silence, by sending a tremor through the invisible geometry that holds every star, planet, and sleeping mind. The first black hole merger ever detected. For almost all of human history, we watched the universe with our eyes before we ever learned that it could be heard. The first detected black hole merger changed that forever. On September 14, 2015, two observatories in the United States, one in Louisiana and one in Washington State, registered a tiny disturbance almost at the same time, separated by only milliseconds. Nothing bright flashed in the sky for ordinary telescopes to see. No star exploded in visible light. No glowing object announced itself. Instead, the signal arrived as a minute's stretching and squeezing of space, so small that it would have been impossible to notice without instruments built with almost absurd precision. This event was later named GB150914, and it came from two black holes that had orbited each other long ago in a distant part of the universe, roughly 1.3 billion years before their final message reached Earth. Each black hole was dozens of times more massive than the Sun, and in their last moments they spiraled together, merged, and became one larger black hole. A portion of their mass was converted into gravitational wave energy, not as a normal explosion of light, but as a ripple in space-time itself. When scientists translated the signal into sound, it became a brief rising note, almost like a cosmic chirp. It lasted only a fraction of a second, yet inside that tiny sound was one of the greatest confirmations in modern science. Einstein had predicted gravitational waves a century earlier, but prediction is not the same as hearing. For decades, these waves were like a sentence written by nature in a language too soft for our instruments. Then LIGO finally heard it. The detectors did not work like ordinary microphones. They used laser beams traveling down long arms, watching for impossibly small changes in distance as a wave passed through Earth. The passing wave made one arm very slightly longer, while the other became very slightly shorter. Then the pattern shifted. The change was far smaller than an atom, yet it carried the fingerprint of two black holes colliding across cosmic history. That is what makes the first detection so powerful. It was not merely the discovery of one event, it was the opening of a new sense. Before this, astronomy was mostly built on light and other electromagnetic signals. After this, humanity had proof that it could study the universe through gravity's own vibrations. We were no longer only looking at the cosmos, we were listening to the motions of space-time, and the most haunting part is how quiet the message was when it reached us. The chirp signal. The sound of two black holes merging is not a roar, but a rising note so brief and strange that it feels like the universe clearing its throat in the dark. Scientists call this signal a chirp, not because black holes make sound in space, but because the gravitational wave pattern, when translated into audio, rises in pitch and intensity like a tiny cosmic whistle. In empty space, there is no air to carry ordinary sound, so nothing is traveling as pressure waves to a listener's ear. What travels is far deeper, a vibration in space-time itself, a pattern of stretching and squeezing that detectors can record, and that humans can later convert into something we can hear. The reason the chirp rises is physical, not decorative. When two black holes orbit each other, they slowly lose energy through gravitational waves. As energy leaves, the orbit tightens. As the orbit tightens, the black holes move faster. As they move faster, the gravitational waves arrive more frequently. That increasing frequency becomes the rising pitch of the chirp. At the same time, the signal grows stronger because the black holes are closer together and disturbing space-time more violently. So the chirp is not just a sound effect. It is the final acceleration of two invisible masses written into a wave. The beginning of the signal is lower and slower, like distant footsteps approaching from a place beyond sight. Then the pitch climbs, the rhythm tightens, the note rises quickly, carrying the last moments of the orbit. Finally, the merger happens, and the sound cuts into a fading ringdown as the new black hole settles into its final form. In that tiny audio shape, scientists can read astonishing information. The speed of the rise helps reveal the masses of the black holes. The strength of the signal helps estimate how far away the event occurred. The final fading tone helps test whether the new black hole behaves the way Einstein's theory predicts. A heavier pair of black holes tends to produce a deeper, shorter chirp. Lighter systems can sing at higher frequencies and may remain in the detector's sensitive range for longer. This means every chirp has a kind of fingerprint. It is not a random noise. It is a biography compressed into less than a second, a final rhythm from objects that cannot be seen directly. And there is something haunting in how small it sounds to us. The merger may release more power in gravitational waves than all the stars in the visible universe emit in light during that instant. Yet when translated into human hearing, it becomes a modest little rising tone, a chirp, a sound almost too simple for what it means. It reminds you that nature does not always announce greatness with thunder. Sometimes the most violent events in the cosmos arrive as a delicate curve in data, a rising frequency, a brief pulse that says, somewhere, long ago, space-time itself was shaken. And by learning to hear that chirp, humanity learned that the universe has a hidden music, not made of air, not made for ears, but made from gravity changing its shape in the final dance of darkness. Ring down, the final vibration after a merger. After the collision, a black hole does not become calm instantly. It quivers, reshapes, and settles like a cosmic bell struck by an invisible hammer. This final stage is called the ring down, and it is one of the most elegant parts of a black hole merger because it turns violence into a fading pattern. When two black holes combine, the result is not immediately a perfectly settled object. For a brief moment, the new black hole is distorted, as if the merger has left ripples in its own shape. It is not a solid body vibrating like metal, because a black hole has no surface you could touch and no material shell that rings in the ordinary sense. The bell metaphor works only because the final black hole relaxes by releasing gravitational waves in a set of fading tones. These tones are not carried by air, and they are not sound waves moving through space. They are patterns in space-time, waves produced as the newly formed black hole sheds its temporary distortions and becomes stable. The remarkable part is that the ring down is not random. A normal bell has a sound determined by its size, shape, and material. A black hole's ring down is determined by its remaining properties, especially its mass and spin. In that fading vibration, scientists can test whether the final object behaves like the kind of black hole predicted by general relativity. If the ring down tones match the expected pattern, it is as if the black hole is giving one last confirmation of its identity. It says, not in words but in gravity, "This is what I have become." The ring down is short, often lasting only a fraction of a second in the detector's data, but it carries enormous meaning. The earlier part of the signal tells the story of two objects spiraling inward. The merger tells the moment of union. The ring down tells the aftermath, the settling, the return to simplicity after chaos. It is the universe's way of letting a disturbed region of space-time smooth itself out. Energy leaves in the form of gravitational waves. The distortions weaken, and the new black hole approaches a quiet final state. This is why ring down is so important for physics. It gives scientists a way to listen for the black hole's final notes and compare them with theory. If future detectors can measure ring down more precisely, they may reveal whether black holes truly relax exactly as Einstein's theory predicts, or whether tiny deviations point toward deeper physics. For now, the ring down feels almost poetic without needing exaggeration. Two dark objects collide with unimaginable force, but the last trace of that event is not an endless crash. It is a fading vibration, a gravitational echo, a final tremor through the fabric of space-time. And maybe that is the quietest lesson hidden in the violence. Even the most extreme merger in the universe has an ending. The chaos does not remain chaos forever. It rings, it fades, it settles, and what remains is a single black hole carrying the silence after the bell. How black holes grow over time. A black hole does not grow simply because matter exists nearby. It grows only when the universe finds a way to deliver mass across one of the hardest boundaries in nature. This is important because the popular picture of black holes eating everything around them makes growth sound automatic, like darkness expanding by appetite. The real process is more selective, slower, and more physical. A black hole increases its mass when energy or matter actually crosses its event horizon. But getting there is not as easy as falling straight down. Gas, dust, stars, and compact objects often carry sideways motion, what physicists call angular momentum, and that sideways motion can keep material orbiting instead of plunging inward. Before matter can become part of the black hole, it usually has to lose some of that orbital motion. In many active systems, gas forms a rotating accretion disk, where friction, turbulence, and magnetic fields help move energy and angular momentum outward, while some material drifts inward. The black hole grows not in one dramatic gulp, but through a long transfer of motion, heat, radiation, and gravity. Some of the falling material never reaches the horizon at all. It can be heated, blown away, or launched into outflows before it crosses the final boundary. This means growth is often inefficient and regulated by the environment. There is even a natural limit to how quickly a bright black hole can gain mass, because radiation from hot infalling gas can push back against new material. If the radiation pressure becomes strong enough, it can slow the inflow. This is one reason the rapid growth of supermassive black holes in the early universe is so interesting. Some of them became enormous when the universe was still young, and scientists still study how their first seeds grew so quickly. They may have started as remnants of massive early stars, or from more direct collapses of large gas clouds, or through combinations of growth channels we are still trying to understand. Black holes can also grow by merging with other black holes. When galaxies collide and settle together, their central black holes may eventually sink toward the shared center, form a pair, and, under the right conditions, merge into a larger black hole. Stellar mass black holes can also merge in pairs, producing gravitational waves and leaving behind a heavier remnant, though some mass energy is carried away by those waves during the collision. Growth, then, is not a single story. It is a history written through accumulation, orbital loss, collisions, radiation, and time. Some black holes remain nearly unchanged for long periods because little material reaches them. Others pass through active phases, brightening their surroundings while gaining mass. A black hole's size today is therefore not just a number. It is the fossil trace of everything its environment allowed to cross the horizon. Every merger that added to it, every period of quiet when nothing arrived, and every burst of activity that changed both the black hole and the galaxy around it. And that is what makes black hole growth so quietly fascinating. The darkest objects in the universe do not grow by hunger. They grow by permission, by the slow rearrangement of matter, motion, and gravity, until a piece of the cosmos can no longer remain outside. Intermediate mass black holes. Between ordinary stellar black holes and the giants that sit in galactic centers, there may be a missing middle class that has spent decades hiding in the dark. These are intermediate mass black holes, and they are fascinating because they seem to occupy the gap between two worlds we understand better. On one side, there are stellar mass black holes, born from the collapse of massive stars, usually carrying a few to perhaps many dozens of times the mass of the Sun. On the other side, there are supermassive black holes with millions or billions of solar masses, settled in the hearts of galaxies like ancient gravitational anchors. But if black holes can grow, merge, and accumulate mass over cosmic history, it feels natural to ask, where are the middle ones? Where are the black holes with hundreds, thousands, or tens of thousands of solar masses? Intermediate mass black holes are often described as a missing link because they could help explain how the first small black holes became the enormous ones we observe in young galaxies. If the early universe already contained medium-sized black hole seeds, then the rapid growth of supermassive black holes becomes easier to understand. But finding them is difficult because they are too small to dominate whole galaxies like supermassive black holes, and too rare or too quiet to reveal themselves as easily as black holes in close binary systems. They may hide in dense star clusters, in the centers of dwarf galaxies, or in places where stars crowd together so tightly that repeated collisions and mergers could build something heavier than a normal stellar remnant. Scientists search for them through indirect clues. Stars moving as if an unseen mass is guiding them, unusually bright X-ray sources that may be powered by a compact object larger than a stellar black hole, or gravitational wave signals from mergers that leave behind black holes heavier than expected. Some candidates are compelling, but the category is still not as cleanly mapped as the smaller and larger black hole families. That uncertainty gives intermediate mass black holes their special atmosphere. They are not fantasy, and they are not settled in every detail. They are a real scientific frontier, where evidence is growing but the full population remains elusive. Part of the problem is that the universe does not label its objects for us. A bright X-ray source might have more than one explanation. A cluster of stars might be influenced by dark remnants, dense stellar matter, or something more complex than a single black hole. A gravitational wave event might suggest a heavy remnant, but it still has to be interpreted carefully. So the search becomes a patient act of elimination, comparison, and measurement. Intermediate mass black holes matter because they may reveal the missing steps in black hole evolution. They could be the quiet bridges between death-born remnants and galaxy-shaping giants. They could show whether supermassive black holes grew from many small mergers, from special early seeds, from dense star clusters, or from several pathways at once. And maybe that is why they feel so haunting. They are not the loudest objects in the story, but they may be the ones that connect the story together. In the darkness between the small and the enormous, between a dead star and a galactic center, there may be a hidden population of black holes carrying the answer to how cosmic monsters first learned to become large, primordial black holes. Some black holes may not have been born from dying stars at all, but from the universe when it was still unimaginably young, dense, and restless. These hypothetical objects are called primordial black holes, and they carry a different kind of mystery from the black holes formed by stellar collapse. A normal stellar black hole needs a massive star to live, burn, run out of fuel, and collapse. A primordial black hole, if it exists, would come from a much earlier chapter, before stars, before galaxies, before heavy elements, when the universe was a hot, rapidly expanding sea of energy and particles. In that newborn universe, tiny differences in density may have existed from place to place. Most of these differences were small, and over cosmic time they helped grow galaxies and clusters. But if some regions were unusually dense, and if conditions were just right, gravity might have overwhelmed expansion locally and squeezed that region into a black hole. This is why primordial black holes are so fascinating. They would not be ashes of stars, but fossils of the early universe itself. Their mass could, in theory, cover a wide range depending on when they formed. Very early formation could produce extremely small black holes. Later moments could produce heavier ones. But here we have to be careful. Primordial black holes are not confirmed objects. They are a serious theoretical possibility, studied because they could help answer deep questions. But no observation has yet proven that a primordial black hole population truly exists. Scientists look for possible signs in several ways. The way gravity from a compact invisible object might briefly magnify a background star, the possible effects of small black holes evaporating through Hawking radiation, the gravitational waves from black hole mergers that might not fit ordinary formation paths, or subtle traces in the structure of the early cosmos. Each clue has to be treated cautiously because other explanations may exist. This is what makes primordial black holes feel so different. They sit between cosmology and black hole physics, between the beginning of time and the darkest objects in space. If they exist, they could reveal details about the first fractions of a second after the Big Bang, especially about how uneven the young universe was. Some researchers have even considered whether primordial black holes could make up part of dark matter because they would be dark, compact, and hard to detect. But observations already restrict many possible mass ranges, so they cannot simply be declared the answer. The honest picture is narrower and more interesting. Primordial black holes may exist in some allowed windows, or they may be rare, or they may not exist at all. Either way, the search matters because it turns black holes into tools for reading the earliest universe. A primordial black hole would be like a sealed relic from a time no telescope can directly photograph, a gravitational fossil left behind before the first star ever lit. And that is the quiet power of the idea. It asks whether darkness could have formed before light had a chance to build galaxies. It asks whether the universe, in its first moments, may have folded some of its own density into permanent shadows. If stellar black holes are the remains of dead stars, primordial black holes would be something far older, not the end of a life, but a memory of the beginning. Could tiny black holes exist? A black hole could, in theory, be smaller than an atom and still carry the gravity of a mountain. But that does not mean tiny black holes have been found. This is where science has to walk carefully between real possibility and imagination. A tiny black hole is not simply a normal black hole viewed from far away. It would be a black hole with very little mass compared with stellar or supermassive black holes. And because the size of a black hole's horizon depends on its mass, its boundary could be unimaginably small. The strange part is that tiny in size does not always mean harmless in concept or easy to make in reality. To compress even a mountain's worth of mass into a region far smaller than a particle is beyond anything ordinary nature does today. Stars make black holes only when enormous amounts of mass collapse under gravity, so a very small black hole would probably need a very different origin. One possibility is the early universe, when density and pressure were extreme enough that unusual regions might have collapsed directly into primordial black holes. Another possibility appears in some speculative theories of physics, where extremely high-energy processes might produce microscopic black holes, but no confirmed evidence shows this has happened. Tiny black holes also have a special relationship with Hawking radiation. The smaller a black hole is, the hotter it should be, and the faster it should lose energy. Very tiny black holes would not sit quietly for cosmic ages. They might evaporate quickly, possibly ending in a burst of high-energy radiation. This is one reason scientists search for unusual gamma-ray signals that could, in principle, come from evaporating primordial black holes. But so far, no signal has been accepted as definite proof. There is also a common fear that particle colliders could accidentally create dangerous microscopic black holes, but this fear is not supported by current physics. If such tiny black holes could be produced at those energies, they would be expected to evaporate almost instantly. And nature has already run far more energetic particle collisions in cosmic rays striking planets and stars for billions of years without catastrophe. The real mystery is not that tiny black holes are monsters waiting nearby. The real mystery is whether the universe ever made them at all. If they exist in certain mass ranges, they could be nearly invisible, passing through space without shining, detectable only through gravity, lensing, or rare high-energy traces. If they do not exist, that absence also teaches us something, because it limits what the early universe could have been like. This is the clean line between evidence and speculation. Tiny black holes are allowed by serious ideas in physics, but they remain unconfirmed. They are not fantasy, yet they are not established objects either. They live in the borderland where theory asks nature a question and observation has not fully answered. Why black holes are not dark matter, at least not simply. Dark matter is one of the few mysteries where black holes seem like an obvious answer at first, and then become much less obvious the longer you look. The idea is tempting. Black holes are dark, compact, hard to see directly, and they affect the universe through gravity, while dark matter is also invisible to light and known mainly through its gravitational influence. So it is natural to ask whether the missing mass in galaxies could simply be made of black holes. But the honest answer is more careful. Black holes may contribute in some limited ways, especially if certain primordial black holes exist, but it is very difficult for ordinary black holes to explain all dark matter. The first problem is timing. Most black holes we know how to make come from stars, and stars formed after the early universe had already begun building the structures we now study. Dark matter, however, seems to have been present from very early times, helping shape the formation of galaxies and the cosmic web before ordinary stars had enough time to create large populations of black holes. That means stellar black holes cannot easily be the original source of all dark matter. The second problem is observation. If dark matter were mostly made of black holes in many mass ranges, their gravity would leave detectable fingerprints. They could bend and magnify the light of background stars in repeated microlensing events. They could disturb wide stellar systems. They could affect the cosmic microwave background by pulling in gas in the early universe and changing the radiation we observe today. They could alter galaxy dynamics in ways that do not match the smooth, widespread behavior dark matter appears to have. Because of searches like these, many possible black hole mass ranges have been strongly limited. There are still narrow possibilities where primordial black holes might make up some fraction of dark matter, and scientists continue to test those windows, especially with gravitational waves, lensing surveys and studies of the early universe. But some possibility is not the same as a complete solution. Dark matter behaves as if it is spread through huge halos around galaxies, forming a broad gravitational scaffolding, not just a collection of rare compact objects shining only by absence. Black holes are also made from collapsed matter or extreme early universe density regions, while many leading dark matter ideas involve unknown particles or fields that do not interact with light in ordinary ways. No single answer has been confirmed, and that is what makes the story so interesting. Black holes are real. Dark matter's gravitational effects are real. The question is whether one can fully explain the other, and so far the universe does not make it that simple. This is a useful lesson in science. The most dramatic answer is not always the most complete one. A black hole is invisible in one way, and dark matter is invisible in another. But invisibility alone does not make them the same thing. The evidence has to match the timing, distribution, abundance, and subtle gravitational traces across the cosmos. So black holes remain part of the dark matter conversation, but not as an easy final answer. They are suspects, perhaps contributors, perhaps clues from the early universe, but not yet the missing matter solved. And in that uncertainty, the mystery becomes deeper. The universe may contain darkness we already understand, like black holes and darkness we still have not named, a hidden mass shaping galaxies from the background while refusing to glow, burn, collapse, or reveal itself in any ordinary form. Black holes and the early universe. The early universe contains a mystery that feels almost like finding a giant tree in a newborn forest. How did some black holes become enormous when the first galaxies were still young? This question matters because black holes are not supposed to become supermassive instantly. Growth takes time. Matter has to lose orbital motion. Gas has to move inward. Radiation can push back against inflow, and mergers require objects to find each other across cosmic distances. Yet when astronomers look far into space, they are also looking back in time, and they have found extremely distant quasars powered by massive black holes that already existed when the universe was less than 1 billion years old. That does not mean physics is broken, but it does mean the story is not simple. In the first galaxies, conditions were very different from the calm spiral structures we often picture today. Gas was more abundant. Galaxies were smaller and more chaotic. Mergers were more frequent, and the universe was denser overall. The first stars may have been much more massive than many stars today because the early universe had almost no heavy elements to help gas cool and fragment into smaller pieces. Some of those first stars could have collapsed into black hole seeds, heavier than many ordinary stellar remnants. But even that may not be enough to explain the largest early black holes unless they grew very efficiently. Another possibility is more dramatic but still scientific. In rare regions, huge clouds of gas may have collapsed more directly, forming much heavier black hole seeds without first becoming normal stars. These are called direct collapse scenarios, and they are attractive because they give the black hole a head start. Instead of beginning with a small remnant and slowly climbing upward, the black hole could begin already thousands or even tens of thousands of times the sun's mass. From there, rapid gas inflow and mergers could help build something much larger. But this is not settled. The early universe does not hand us a clear recording of what happened. Scientists must reconstruct the story from distant light, galaxy surveys, quasar spectra, simulations, and the growth patterns of black holes across cosmic history. The challenge is to explain not only that giant black holes existed early, but how often they formed, where their first seeds came from, and how they influenced the young galaxies around them. This makes early black holes more than rare objects. They are clues to the childhood of structure itself. They may have heated gas, shaped star formation, and helped regulate the galaxies that were still assembling around them. The mystery is not simply that black holes grew large. It is that they grew large while the universe itself was still learning how to build galaxies. And that thought is quietly astonishing. In the first billion years, while the cosmos was still young, dark centers were already forming, feeding, shining through quasars, and leaving marks on the architecture of everything that came after. The early universe was not only a place where the first stars turned on, it may also have been a place where some of the deepest shadows began, growing almost as soon as light had something to shine upon. How supermassive black holes formed so early. The puzzle is not that supermassive black holes exist. The puzzle is that some of them seem to have arrived too early for the universe's clock. When astronomers find extremely distant quasars, they are not only finding bright objects far away, they are looking back toward a time when the cosmos was still young, when galaxies were still assembling, gas was still settling into structure, and the first generations of stars had only recently begun changing the chemical story of space. Yet inside some of those early quasars, the engine appears to be a black hole with millions or even billions of times the mass of the Sun. That creates a cosmic time problem. A black hole cannot become supermassive by magic. It needs a beginning, a seed, and then it needs growth. But growth is not unlimited. Gas does not fall inward perfectly. Radiation from hot material can push outward. Turbulence, star formation, explosions, and galactic motion can interrupt the supply. Even mergers take time, because black holes first need galaxies or star clusters to bring them together. So the question becomes sharp. How did these objects gain so much mass before the universe had much time to give them? One possible answer is that the first seeds were heavier than ordinary stellar black holes. If the earliest stars were extremely massive, their deaths could have left behind larger remnants than many black holes born today. Another possibility is even more direct. Under rare conditions, a huge cloud of pristine gas may have collapsed toward a black hole seed without first breaking into many normal stars. This would give the black hole a head start, beginning not as a small remnant, but as something already massive enough to grow quickly. A third possibility is that early black holes sometimes grew faster than the simple steady limit we often use, because thick flows of gas may have trapped radiation and allowed material to keep moving inward more efficiently for a time. This is called super Eddington growth, and it is not a free miracle. It requires special conditions and probably cannot happen everywhere. Mergers may also have helped, but mergers alone may not solve the problem, because they depend on black holes finding each other, sinking together, and combining within crowded young environments. The real answer may not be one pathway. It may be a mixture. Heavy seeds in rare regions, intense gas inflow, chaotic young galaxies, and occasional mergers all working together in the densest parts of the early universe. That is what makes the mystery so powerful. These black holes are not just large objects. They are clocks. Their mass tells us how much growth must have happened, and their distance tells us how little time was available. Black holes and galaxy evolution. A galaxy and its central black hole can grow like two lives shaped by the same storm, not one master controlling the other, but two systems tied together by gravity, gas, motion, and time. This is the heart of black holes and galaxy evolution. The largest galaxies often contain supermassive black holes at their centers, and those black holes seem to have grown alongside the stellar cities around them. The connection is not simple. A black hole is tiny compared with its host galaxy in physical size, almost like a dark seed at the center of an enormous glowing island. It does not reach out and pull every star like a puppeteer. Most stars in a galaxy orbit because of the gravity of the galaxy's total mass. Stars, gas, dark matter, and all the matter spread across vast distances. Yet when astronomers compare many galaxies, they find something remarkable. The mass of the central black hole often relates to the properties of the galaxy's central bulge, especially the motions of stars near the core. This suggests that black holes and galaxies do not evolve as completely separate things. They share a history. One reason is gas. Gas is the raw material for both star formation and black hole growth. When galaxies merge, collide, or become gravitationally disturbed, gas can be driven inward. Some of it forms new stars. Some of it may move closer to the central black hole. During these active phases, the black hole's surroundings can shine as an active galactic nucleus, releasing energy from material before it crosses the horizon. That energy can then affect the galaxy around it. Radiation, winds, and powerful jets can heat gas, push it outward, or prevent it from cooling efficiently. And if gas cannot cool, it cannot easily collapse into new stars. In this way, a black hole can influence the rhythm of star formation, not by ruling every star directly, but by changing the conditions of the gas from which future stars would be born. This process is called feedback, and it is one of the key ideas in galaxy evolution. Feedback can sound destructive, but it is more subtle than destruction. Sometimes it slows growth, sometimes it redistributes gas, sometimes it may even compress material in certain regions and help trigger star formation locally while preventing it elsewhere. The relationship is not a simple battle between light and darkness. It is more like a long negotiation between fuel and energy. A galaxy provides the material that can grow the black hole, and the black hole, when active, can reshape the galaxy's ability to keep making stars. This may help explain why some massive galaxies eventually become quiet, filled mostly with older stars, no longer forming new ones at the same pace. Their central black holes may have helped heat or remove the gas that would have kept the galaxy young. But scientists are careful here. Galaxy evolution has many causes, including environment, mergers, dark matter halos, supernovae, and the supply of cold gas. The black hole is not the only actor. It is one powerful participant in a much larger cosmic ecology. And that is what makes the idea beautiful. A black hole, often imagined as an isolated darkness, may actually be woven into the life cycle of its galaxy. Its growth records moments when gas flowed inward. Its activity can mark periods when the galaxy changed direction, brightened, slowed, or transformed. The galaxy builds the black hole. The black hole helps change the galaxy. Neither is the whole story alone. Together, they reveal that cosmic evolution is not only about objects getting bigger over time. It is about relationships, exchanges, limits, and feedback loops written across millions of years. At the center of a galaxy, darkness may not be an absence from the story. It may be one of the forces helping the story decide how many stars will be born, how long the galaxy will remain active, and when its bright youth will begin to settle into a quieter age. When black holes stop star formation. A galaxy can be full of gas and still stop making new stars, if its central black hole keeps that gas too warm to collapse. This is one of the strangest ways black holes influence the life of galaxies. Not by reaching out to destroy stars that already exist, but by changing the future supply of star-making material. Stars are born when gas becomes cold, dense, and unstable enough for gravity to gather it into clouds, knots, and eventually glowing cores. Cold gas is the quiet nursery of a galaxy, but when a supermassive black hole becomes active, the region around it can release enormous energy before material crosses the horizon. Some of that energy emerges as radiation, some of it appears as winds, and in many powerful galaxies, some of it is carried by narrow jets of high-speed particles launched from the black hole's surroundings, guided by magnetic fields and driven by the violent motion of matter near the center. These jets do not come from inside the black hole itself. They come from the extreme environment outside it. But once launched, they can travel far beyond the central region, piercing through gas around the galaxy and even into the larger halo of hot material surrounding it. Instead of simply blasting everything away like an explosion, the jets can inflate huge bubbles, carve cavities, stir turbulence, and send pressure waves through the gas. Astronomers have observed such cavities in hot X-ray gas around massive galaxies and galaxy clusters, places where jets appear to have pushed material aside and injected energy into the surrounding atmosphere. The result can be a kind of cosmic heating system. Gas that might otherwise cool and fall inward stays too energetic, too stirred, or too spread out to form stars efficiently. This is sometimes called feedback, but here it feels almost like a thermostat. When gas begins to gather near the center and feed the black hole's environment becomes active. That activity sends energy back outward. The outward energy limits the supply of cold gas, and star formation slows. The galaxy does not die in a single moment. It fades into quietness over long periods, forming fewer young stars while older stars continue to glow. This may help explain why many massive elliptical galaxies are filled with old stellar populations and very little new star formation, even though they can sit inside enormous reservoirs of hot gas. The gas is present, but presence is not enough. It must cool, it must condense, it must lose pressure and settle into the right conditions. A black hole's jets can keep interrupting that process, like a deep central engine preventing the galaxy from returning to youth. The idea is powerful because it changes how we think about darkness. A black hole is often imagined as an ending, but in galaxy evolution, it can act more like a regulator, deciding indirectly whether future generations of stars will be born. It does not need to touch every cloud. It only needs to alter the temperature, motion, and pressure of the gas that would have become those clouds. And that makes the story quietly unsettling. Some galaxies may grow old not because they ran out of material, but because their own centers learned how to keep that material from becoming stars. In the long life of a galaxy, the black hole is not just a hidden mass. It can become a keeper of silence, heating the very fuel of creation, until the bright nursery of new suns slowly falls asleep. Tidal disruption events. Sometimes a galaxy that looked quiet for years suddenly brightens, because one unlucky star came too close to the dark center it could not understand. This rare cosmic event is called a tidal disruption event, and it happens when a star passes near a massive black hole, closely enough that gravity no longer pulls on the star as one whole object. The side of the star facing the black hole feels a stronger pull than the far side. And if that difference becomes larger than the star's own gravity holding it together, the star begins to tear apart. It is not swallowed neatly. It is stretched into long streams of gas, some escaping outward into space and some falling back toward the black hole. That returning material can collide with itself, heat up, spread into a temporary disk or flow, and release a bright flare of light. For astronomers, this flare is precious because many supermassive black holes are normally quiet. They may sit in galactic centers with little gas nearby, almost invisible unless something disturbs them. A tidal disruption event is like a sudden lamp turning on around a hidden object. It allows scientists to detect black holes that were not actively shining before, to estimate their mass, and to study how matter behaves when it is violently rearranged by extreme gravity. The light from these events can appear in ultraviolet, optical, X-ray, and sometimes radio wavelengths, depending on how the torn material heats, spreads, and interacts with its surroundings. The brightness may rise and fade over months or even years, not because the star is burning like a normal stellar explosion, but because its debris is returning and releasing energy as it moves through the black hole's environment. This makes tidal disruption events different from supernovae. In a supernova, a star dies because of its own internal evolution. In a tidal disruption event, the star may have been ordinary until its path carried it into a region where gravity became uneven enough to undo it. And not every star near a black hole is destroyed. Some pass safely at greater distances. Some may be partially stripped and survive, leaving behind a damaged remnant. Others cross the danger zone so deeply that their structure is lost completely. The black hole's mass matters too. Around certain very massive black holes, a star might pass inside the event horizon before it is torn apart in a visible way, making the event harder or impossible to observe from outside. So the brightest tidal disruption events often happen in a delicate range where the black hole is massive enough to disrupt the star strongly, but not so massive that the entire process is hidden too soon. That balance gives these events their strange beauty. They are rare accidents of orbit, gravity, timing, and scale. A star spends millions or billions of years shining by its own internal fire, and then, in one close passage near a galactic center, its future changes into a glowing stream of matter. What was once a sphere becomes a ribbon. What was once steady light becomes a flare. What was once hidden gravity becomes visible through destruction. And the lesson is not simply that black holes can tear stars apart. It is that the universe sometimes reveals its darkest objects through the brief suffering of something bright, turning a silent galactic center into a temporary signal that says, here, in the quiet, gravity was waiting. Microlensing and hidden black holes. A hidden black hole can announce itself without shining at all, simply by borrowing the light of a star behind it. This is the quiet power of microlensing, a method that turns gravity into a temporary magnifying glass. A black hole may be completely dark on its own, with no glowing disk, no companion star, no jet, and no obvious signal. But if it drifts across the line of sight between Earth and a more distant background star, its gravity can bend the star's light on the way to us. The black hole does not create the light, and it does not touch the star. It changes the path the light takes through space. For a while, the background star appears brighter, not because the star itself has changed, but because the invisible mass in front has focused more of its light toward us. This brightening can rise smoothly, reach a peak, and then fade again as the alignment passes. To a telescope, it may look like a star briefly swelling in brightness for no ordinary reason. The color of the star usually stays nearly the same, which is important, because many real stellar outbursts change color as they heat or cool. Microlensing is different. It is a gravitational event, not a flare from the star itself. The duration of the brightening can reveal clues about the lensing object, its mass, its motion, and its distance, though these are not always easy to separate. A heavier compact object can create a longer event, while motion and geometry also affect the timescale. In the best cases, astronomers can also detect a tiny shift in the apparent position of the background star, a subtle wobble caused by the lens bending the light asymmetrically. This is called astrometric microlensing, and it can help estimate the mass of the invisible object more directly. If the lens has enough mass, produces no detectable light of its own, and cannot easily be explained as a faint normal star, white dwarf, or neutron star, then an isolated black hole becomes a serious possibility. That is what makes microlensing so valuable. It can reveal black holes that are not feeding, not merging, not glowing, and not orbiting a visible companion. It offers a way to find the quiet wanderers, the black holes moving through the galaxy without dramatic behavior. But the evidence must be handled carefully. A microlensing event alone does not automatically prove a black hole. Many dim objects can bend light. Scientists need detailed measurements, long observations, and careful modeling to decide what kind of object caused the lensing. This patience is part of the beauty of the method. Microlensing does not show you the black hole as an image. It shows you the black hole as a temporary distortion in someone else's light. It is like discovering an invisible person in a dark room, because a candle flame behind them briefly bends and brightens in an impossible way. And that is the deeper lesson. Not everything real has to glow, collide, or speak loudly. Some objects reveal themselves only by how they alter the paths of other things. A hidden black hole may pass silently between Earth and a distant star, and for a brief time the universe gives us a clue. A brightening, a shift, a small gravitational signature, as if darkness has crossed in front of light and left its fingerprint without ever becoming visible. Black holes wandering between stars. Somewhere between the stars, there may be black holes moving quietly through the galaxy with no light around them, no bright disk, and no companion to reveal their path. These wandering black holes are not monsters roaming with intention. They are natural remnants of massive stars that ended their lives and were left behind as compact darkness. If the explosion that formed one of them was uneven, the newborn black hole may have received a kind of gravitational kick, sending it onto a new path through the Milky Way. In other cases, a black hole may once have belonged to a binary system, but a stellar explosion or close gravitational encounter broke the partnership apart, leaving the black hole to continue alone. So, wandering does not mean moving outside the laws of the galaxy. It means orbiting through the Milky Way like other unseen masses do, following the broad gravitational field created by stars, gas, dark matter, and the galaxy's structure. The calm mystery is that these objects can be incredibly difficult to find. A black hole that is not pulling material from a nearby star, not surrounded by a hot accretion disk, and not merging with another compact object may produce almost no signal at all. It can pass through interstellar space as a hidden weight, present but nearly silent. The Milky Way may contain millions of stellar mass black holes, because many massive stars have lived and died across its history. But only a small fraction are obvious to us. Most may be quiet remnants drifting through the galactic dark, separated by enormous distances, not close enough to disturb our world, and not dramatic enough to announce themselves. This is important to understand. A wandering black hole is not dangerous simply because it exists. Space is vast beyond intuition, and the chance of one passing near Earth is extremely small. Even if one crossed the galaxy near other stars, its influence would be limited by distance, just like any other mass. Gravity is powerful, but it is not magic. It weakens with separation, and most wandering black holes would pass through the emptiness between stars without causing visible chaos. What makes them fascinating is not fear, but hidden history. Each one may carry the final trace of a star that once burned brightly, perhaps inside a cluster, perhaps in a binary pair, perhaps in a region of the galaxy that has since changed completely. It may have traveled for millions or billions of years, crossing spiral arms, moving above or below the galactic disk, passing through regions of dust and starlight without ever becoming visible. Scientists search for such objects through their effects rather than their glow. A background star that briefly brightens because gravity bends its light, a subtle shift in a star's position, or a faint hint of material being disturbed as the black hole moves through thin gas. But even then, certainty is difficult because darkness has many disguises and every clue must be measured carefully. Wandering black holes remind us that a galaxy is not only made of what shines. Rogue black holes. A rogue black hole is not just hidden, it is displaced, cut loose from the place that once gave its motion a story. Unlike a black hole resting in a galactic center, or one still locked in a close dance with a companion star, a rogue black hole may have been thrown away by violence, imbalance, or gravitational chance. The word rogue can sound dramatic, but it does not mean the black hole has intention, hunger, or direction of its own. It means it is no longer comfortably tied to the system that made it visible or predictable. Some rogue black holes may begin as stellar remnants inside binary systems. If one star explodes unevenly, the sudden loss of mass and the asymmetric kick from the explosion can break the pair apart, sending the new black hole onto an independent path. Others may be pushed out of dense star clusters, where many massive objects pass close together and exchange energy like silent billiard balls under gravity. In such crowded places, a black hole can gain speed through close encounters and be flung outward, leaving behind the cluster where it formed. On even larger scales, entire galaxies can create rogue or recoiling black holes. When two galaxies merge, their central supermassive black holes may eventually come together as well. If the merger releases gravitational waves more strongly in one direction than another, the final black hole can receive a recoil kick. In some cases, it may be shifted away from the galaxy's center. In extreme cases, it could be launched into the outskirts or beyond, carrying millions of solar masses through space like a dark engine without a home. This is one of the most haunting possibilities in astrophysics, not because it threatens us, but because it shows that even the central anchors of galaxies are not always perfectly fixed. A rogue black hole is difficult to find because its usual clues have been stripped away. If there is no rich supply of gas around it, it may not shine. If it has no companion, it may not reveal itself through an orbit. If it moves through thin space, it may leave only faint gravitational traces. A possible lensing event, a disturbed patch of gas, or, in the case of a recoiling supermassive black hole, an active nucleus strangely offset from the center of its host galaxy. Each clue must be treated carefully because the universe has many ways to imitate mystery. But the idea itself is real enough to be taken seriously. Gravity can eject its own creations. Systems can break, centers can move, objects that once belonged can become travelers, and there is a quiet loneliness in that. A rogue black hole may carry the memory of a star cluster, a dead binary, or a galaxy merger, but it does not carry that memory as light. It carries it as velocity, mass, and direction. A biography reduced to motion through darkness. It may drift for millions or billions of years, not as a monster hunting worlds, but as an orphaned remnant of a violent past, crossing regions where no eye would notice unless light or gas happened to pass near enough to betray it. The deeper lesson is that space is not only filled with shining structures, it also contains things that have been removed from structure, objects unmoored from the bright communities that formed them. A rogue black hole is cosmic loneliness made physical, a collapsed history moving through the dark, almost silent, almost invisible, reminding us that the universe does not only build homes for matter, sometimes it also sends its deepest shadows wandering away from them. Could a black hole ever threaten Earth? The safest way to fear a black hole is to understand how much space is actually between us and one. A black hole could threaten Earth only under very specific conditions. It would have to come extremely close, close enough for its gravity to seriously disturb the orbits of planets, the Sun, or nearby objects in the solar system. That is not what astronomers see. There is no evidence of a black hole on a dangerous path toward Earth, and the known black holes in our galaxy are separated from us by vast distances. This matters because black holes do not reach across space like cosmic traps. Their gravity follows the same basic rule as any other mass. Distance matters enormously. A black hole 10 times the mass of the Sun is not dangerous because it exists somewhere in the Milky Way. It would only become a problem if it passed close enough for its gravity to compete with the Sun's influence here, and space is so empty that such encounters are extraordinarily unlikely. The Milky Way may contain many stellar mass black holes, but they are scattered through a galaxy more than 100,000 light-years across. Most of them move through space as quiet remnants, not as roaming disasters. Even a wandering black hole would usually pass through the enormous gaps between stars without dramatic effects, because those gaps are not small empty rooms. They are immense distances almost beyond human scale. If one did pass near a star system, the first danger would probably not be a dramatic swallowing scene, but gravitational disruption, altered orbits, disturbed comets, changed paths of planets, or stress on objects that had once moved calmly. But that requires proximity, and proximity is the rare part. The supermassive black hole at the center of the Milky Way is also not a threat to Earth. It is massive, yes, but it is about 27,000 light-years away, locked in the galactic center, not traveling toward us like an approaching storm. Earth orbits the Sun because the Sun dominates our local gravitational environment, and the galaxy's central black hole is far too distant to pull our planet out of its ordinary path. The same calm realism applies to black holes created by dying stars. They do not suddenly expand through space. They do not turn the whole surrounding region into an unstoppable suction zone. If a star far away becomes a black hole, the danger to Earth depends on distance, radiation from the stellar death, and cosmic environment, not on the black hole magically reaching us afterward. A nearby supernova could be dangerous in other ways, but that is a different question from a black hole itself threatening Earth. So the real answer is reassuring without becoming careless. Black holes are among the most extreme objects in the universe, but there is no known nearby black hole danger to our planet. Their power is real, but it is local. Their mystery is enormous, but their threat is not everywhere. And perhaps that is the lesson that makes them more fascinating than frightening. The universe can contain objects so dense that light cannot return from them, while also being spacious enough that we can study them from a safe distance. Fear makes black holes feel close. Understanding puts them back where they belong, far away, rare in their dangerous alignments, and important not because they are coming for us, but because they reveal what gravity can become when nature is pushed to its deepest limits.